Given the billions of years of evolution for the universe, life elsewhere in the universe has undoubtedly emerged. Albert Einstein once said that with so many Earth-like planets out there, there must be life somewhere else in the universe. We're not alone. A recent survey by Pew Research Center found that 2/3 of Americans believe aliens exist. Over half think that UFOs seen by military people are probably signs of intelligent life from other planets. Thanks to big improvements in space science, scientists are now more hopeful than ever that we might find alien life in the next few years. One of the well-known astronomers at Search for Extraterrestrial Intelligence has confidently expressed that within the next 20 years, we will definitely find clear proof of intelligent life beyond Earth. As we continue to explore the vast universe and discover thousands of new planets, one old question still haunts us: is anyone else out there? The huge size of the universe, filled with countless galaxies, stars, and planets, makes it clear that there could be life somewhere else, even if life starting on Earth was a rare event. The universe is so big that it's like a vast blank canvas where many different forms of life could appear. This might include all kinds of intelligent beings, from the simplest to the most advanced. Imagine floating alone in the endless quiet of space. It might feel silent and empty, and you might think you're completely alone. But remember, inside our bodies, there are many small ecosystems we often overlook. Countless tiny organisms and microbes live on our skin and in our guts, even though we don't notice them. These tiny creatures might not be smart like us, but their presence shows that we're never truly alone. This suggests that many forms of life may exist in the universe. Given the age of the universe, it's possible that various life forms could exist elsewhere. On planets far away, creatures might have developed amazing mental abilities because of their unique environments and evolution. Some of these alien civilizations might be less developed, similar to how humans were long ago. They might know simple ways to communicate, use basic tools, and have a limited understanding of the universe. But other civilizations could be far more advanced than us. These aliens might have incredible intelligence, mastering advanced technology and space travel. Their knowledge and culture might be so far beyond ours that they seem almost like gods to us. The diversity of intelligence in the universe goes beyond our imagination. In truth, what we think of as progress might look very small compared to the whole galaxy. To better understand how vast the universe is, and our place in it, scientists and thinkers use different scales and methods. One method, called the Kardashev scale, was created by Russian scientist Nikolai Kardashev in 1964. It helps classify civilizations by how much energy they use and how advanced their technology is. This scale is a useful tool for thinking about where we might be heading as a species. The Kardashev scale is a system with 4 levels that ranks civilizations by how well they can use energy. It's based on the idea that the more advanced a civilization's technology is, the more energy it can use. A Type 1 civilization, also called a planetary civilization, can use all the energy available on its home planet. This means they use things like solar, wind, and geothermal energy to run their industries and meet their energy needs. They can control the resources of their entire planet. A Type 1 civilization is not limited to a single planet, but has established a presence on multiple planets and moons. Within their solar system, they have formed a unified government that spans across these planets and enables interplanetary trade, research, and collaboration. Their technological advancements have enabled them to augment themselves and their capabilities. A Type 2 civilization, also known as a stellar civilization, can use the energy from their own star. They might build huge structures like Dyson spheres or Dyson swarms that surround their star and capture its energy. This type of civilization can use the huge resources of their solar system to power their advanced technologies and explore other stars. Each tenth of a number in the Kardashev scale equates to an order of magnitude of power utilization potential. A type 2 has 10 orders of magnitude more power at its disposal than a type 1, or alternatively worded 10 billion times as much power, the same difference in power between a nuke and a toddler's punch. A type 3 civilization, also known as a galactic civilization, can use the energy from their entire galaxy. They might be able to move planets, use stars to power black holes, and even change the structure of space-time. And at the last, a Type 4 civilization would be capable of creating a universe itself, meaning multiverse, and can control these universes. Imagine a scale that measures how advanced a civilization is based on how much energy they can use. We're not even at the level 1, but we're definitely using more energy than ever before. Some scientists say that if we keep increasing our energy use by 3% every year, it could take between 100 and 200 years to reach Type 1. At that point, we'd be able to harness all the sun, wind, and water power we could ever want. Imagine controlling the weather, even building cities that float. That's the kind of power we might have in the future. Just like civilizations use different amounts of energy, they probably also use different ways to talk to each other. Imagine a civilization that can use all the power on their planet. They might still rely on radio waves or light signals to send messages, like we do today. But as civilizations get even more advanced, they might invent totally new ways to communicate, faster and more complex than anything we can imagine. Imagine civilizations so advanced they can harness all the power from their star. Type 2, civilization might be sending messages through ripples in space-time or using some mind-blowing tech called quantum entanglement. And Type 3 civilization might be using shortcuts like wormholes or even talking through some kind of space tunnel to travel to other galaxies. As we started our journey toward becoming a Type 1 civilization, we first tried to reach out to outer space. We sent messages in different forms to say hello and show our curiosity about the universe. One of the first big efforts to talk to aliens was the Voyager Golden Records. The Voyager Golden Record, put together by a team led by Carl Sagan, included sounds, pictures, and music from Earth to show the variety of life and cultures we have. The Voyager space probe is now 14 billion miles away from Earth, making it the farthest object we have sent into space. It carries messages that show our curiosity and wish to make contact with others in space. However, sending these messages comes with big challenges. Space is incredibly vast and mostly empty, which makes it very hard for any alien civilization to find our small plaques and records by chance. The huge distances make it unlikely that these messages will ever meet anyone out there. The vast distances between stars and planets mean that messages we send into space could take hundreds or even thousands of years to reach their destination. For example, if anyone ever found the Voyager Golden Records and replied, their message would take ages to get back to us. These long times make it very hard to have quick conversations or share information quickly with beings from other stars, limiting our chances for fast communication and learning from each other. Scientists around the world use radio telescopes to search the skies. They look for the special, narrowband signals that are different from the usual noise in space. These telescopes help scientists listen to the universe's faint signals. It's similar to how you tune into a specific station on your FM radio. Scientists often look for signals in a part of the radio spectrum called the water hole, which includes frequencies close to those naturally emitted by hydrogen and hydroxyl. These elements are common in the universe, making their frequencies good choices for trying to communicate across space. A big challenge we face is the language barrier. Language is fundamental for humans to share ideas, feelings, and knowledge. But when it comes to communicating with extraterrestrial beings, understanding their language becomes tricky. How can we interpret the signals or codes from an alien civilization? What methods might they use to communicate? These are the key questions that scientists and researchers deal with in their search for extraterrestrial intelligence. Mathematics is often considered a universal language, one that goes beyond cultural and linguistic differences. By using mathematical concepts, we might find a way to communicate with alien civilizations. Basic ideas like addition, subtraction, multiplication, and division apply everywhere and could provide a foundation for exchanging messages with beings from other worlds. No matter where you are in the universe, some basic truths remain the same, such as 2 plus 2 equals 4, and the ratio of a circle's circumference to its diameter is about 3.14. Even if different civilizations use different symbols for numbers, the basic maths concepts don't change. One way we might communicate with aliens using maths is through bits. In digital communication, a bit is the smallest piece of information and can be a 0 or a 1. By putting together a series of bits, we can create and send messages. For example, we could assign a unique series of bits to each letter of the alphabet, creating a binary code for written communication. In this code, 1 bit could represent the letter A, 2 bits could represent B, and so on. This binary code could be a starting point for communication, allowing us to send longer messages that might be understood by an intelligent alien civilization. Using this method shows aliens that we understand maths. However, crafting a message that aliens can understand would be one of the biggest intellectual challenges humans have ever faced. Actually, having a conversation with aliens might be extremely difficult, if not nearly impossible. Even if there are potential risks in reaching out, it's too late to hide our existence. Any civilization capable of traveling between stars could already detect the radio and TV signals that have been escaping into space from Earth. Sending signals through active SETI projects doesn't really increase our risk. Given what we know now, it's possible that we might make contact with another civilization soon. It's also possible that a civilization has already heard our messages but chosen not to respond, perhaps because they prefer it that way. All these efforts are part of what's called active SETI or METI, which stands for Messaging Extraterrestrial Intelligence. This involves deliberately sending messages or signals from Earth into space. By actively trying to communicate, scientists hope to catch the attention of intelligent beings who might be listening and able to receive these signals. Moving from just watching to actively sending messages shows a growing belief that humanity should take an active role in trying to make contact with other civilizations. Nevertheless, we have yet to find any evidence of aliens. This problem is known as the Fermi Paradox, named after the renowned physicist Enrico Fermi. During a lunch conversation with his colleagues, Fermi famously asked a simple yet profound question. So where is everybody? This question highlights the puzzling absence of any confirmed contact or evidence of alien civilizations, especially given the vast number of places they could potentially exist. It's possible that more advanced civilizations simply choose not to communicate with us. Given our current level of development, they might not see a reason to. The technology needed for interstellar travel would likely be available only to civilizations that have reached at least a Type 2 level, and from their perspective, we might not seem significant enough to engage with. It's like asking why a person would try to have a meaningful conversation with ants. How would an ant even recognize that someone is trying to communicate with it? Compared to these advanced civilizations, we might seem like highly developed ants that have taken over a planet. This idea is known as the zoo hypothesis. It suggests that extraterrestrials might have decided not to contact us or reveal themselves for several reasons. They might want to let us develop and evolve on our own without interference. They could also be trying to avoid potential conflicts or cultural clashes, or they might simply not be interested in communicating with a civilization that's less advanced than theirs. Another explanation for the Fermi paradox might be that we have already received signals from other civilizations, but we didn't recognize them. Maybe we haven't noticed these signals, or we don't have the ability to understand or decode them yet. There have been some unusual signals detected from space that are still being studied, raising big questions for scientists. One of the most well-known of these signals was detected in 1977 by the Big Ear radio telescope at Ohio State University. During a search for signals from other civilizations, they detected a strong, unusual signal spread across a frequency range. On the night of July 15, 1977, Jerry Amon, a professor at Ohio State University and a volunteer for the SETI project, was monitoring the signals. He noticed a strange signal recorded by the computer on a printout. This signal later turned out to be the strongest unusual signal ever picked up by a radio telescope at that time. The signal lasted for 72 seconds and was 30 times stronger than typical background signals. It originated from the direction of the constellation Sagittarius. The computer translated the received signals into a series of alphanumeric characters, creating the now famous sequence 6EQJ5. This suggested that the source of the sound was broadcasting regularly, similar to how a lighthouse beam sweeps across the sea, lighting up different areas as it rotates. It seemed as though we caught a glimpse of the signal when we were facing it and then lost it as we turned away. However, the signal was not consistently detected. Because of the design of the Big Ear telescope, there was a delay of a few minutes before its second receiver could check the same area of space from which the WOW signal originated. By the time it was able to look, the signal had disappeared. In fact, the signal was so astonishing that when the technician reviewed the printout the next morning, he wrote WOW in the margin. This reaction led to the name WOW signal, which has continued to intrigue the international scientific community to this day. It's possible that someday we might detect another signal like the WOW signal and discover it's not of alien origin. However, there's an important technical approach to consider. If I were leading the research, I would aim my telescope at the part of the sky where the WOW signal was detected and kept there for an extended period. This way, if any other signals were to come from that same area, I wouldn't miss them. However, it's important to consider how the Big Ear telescope was designed. In order to find evidence of alien life, researchers at Ohio State University prepared a special telescope named Big Ear as part of their quest to find evidence of alien life. This is significant because it raises the possibility of confirmation bias influencing their findings. Big Ear was huge, about the size of 3 football fields. It functioned similarly to modern telescopes. It captured signals with a large mirror at one end, which then bounced them off smaller mirrors at the other end. The signals were directed into 2 receivers in the middle where the data were processed. You may notice that these capture dishes are just wireframes though, not true mirrors. This is because Big Ear was a radio telescope. It wasn't trying to see with visible light. Big Ear was more limited in its motion compared to a telescope that could rotate freely. It could only tilt its primary reflector up and down, so it could only focus on a narrow strip of space at a time. This design was cheaper and easier to build. However, the designers had a clever idea to overcome this limitation. They built Big Ear in such a way that the rotation of the Earth would move it left and right, with the Earth's rotation handling one direction and the tilting reflector adjusting along the other axis. Big Ear could eventually point to any spot in the sky if you waited long enough. It was a smart solution to its design constraints. But consider the way Big Ear was constructed. It moves with the rotation of the Earth, so it can't continuously monitor the same spot in the sky for more than a few moments. This limitation means we don't know if more signals came from that area of space. It's possible that numerous signals, even something as complex as an entire orchestra performance, could have been broadcast from that region in the hours following the wow signal. But since Big Ear wasn't focused on that spot for more than a brief moment, it might have only caught a single note from the potential symphony of signals. This approach highlights a deliberate choice by organizations like SETI, which are searching for intelligent life in the universe. Because resources are limited and space is vast, they can't afford to point a telescope at a single spot for decades, hoping aliens will respond from that location. Instead, they prefer to sweep across wide areas of space to cover as much ground as possible, hoping to get a lucky hit. It's like fishing. Rather than leaving their line in the water at one spot, they keep casting and casting, seeing if anything bites right away, and moving on if nothing does. This approach is more reasonable than an analogy makes it sound, as aliens are not fish to be attracted to a lure or scared off by a splash of a telescope looking at them. And although the first process is more methodical, there's every chance that if you just sweep your telescope across the sky, you will encounter some evidence or signal. The problem comes with the follow-up. There have actually been numerous signals, like the wow signal that radio telescopes have picked up over the years, strange and unusual bursts that we have no current explanation for. But because we aren't focusing on them and thoroughly following up over years of continued dedicated study, we are missing a lot of information, and as a result, we end up with weaker conclusions. Which brings us to our conclusion. Perhaps we are seeing no intelligent life simply because of our method. Of course, these are just a few of many possible theories. For this video, I've focused on some of the technical challenges in finding signs of alien life. However, there are also many theory-based explanations that are more speculative. These theories are fascinating and offer intriguing insights into our own civilization. If you enjoyed this topic, I'll explore these theories in another video. Do you think there are aliens up in the night sky? If so, why do you think they've not spoken to us? Eamon and his team thoroughly investigated the signal and confirmed that it wasn't caused by any interference from Earth. Despite their efforts, when the radio telescope operators tried to detect the signal again over the next month, they couldn't find it. Since then, astronomers have repeatedly scanned the same part of the sky, hoping to detect the wow signal once more, but it has never reappeared. Today, the origin of that signal is still a mystery. Our galaxy alone has hundreds of billions of stars, and there are billions of galaxies in the universe. Even if life exists on just a tiny fraction of those planets, it means life is widespread throughout the universe. Driven by curiosity and a thirst for exploration, humans have begun the search for intelligent life, hoping to find it or be found. The first contact might not happen in our lifetimes, but whenever it does, it will be a monumental event for humanity. What will happen after that? What will it mean if we receive and confirm a signal from extraterrestrials? How would this impact our lives, our priorities, our view of the world, and our own identity? Will we be ready for such a discovery? The real challenge for SETI research is to find a signal as striking as the wow signal that can be detected consistently, not just once. This repeatability would be crucial for confirming the existence of extraterrestrial intelligence. For us to find or contact an alien civilization, one of two things needs to happen. Either we send a message and they reply, or they send a message to us first. There are different ways to do this, like sending spaceships or unmanned probes, but sending spaceships is very difficult. At the speeds our spaceships can go, it would take millions of years to reach another star. For example, the Voyager 2 probe took about 49 years just to leave our solar system. The closest star is 4 light-years away, which would take over 81,000 years to reach with our current technology, about 2,700 human generations. And that's assuming the nearest aliens are at that closest star. Even if our technology improves, it takes a huge amount of energy to accelerate something to the speed of light. Actually, it would take more energy than exists in the universe. Objects just can't travel that fast. So, unless we or aliens find a new way, the easiest way to communicate is by sending radio signals. It's possible that this speed limit will be broken someday. Scientists have some ideas, like moving space around you with warp bubbles instead of moving yourself. The speed of light limit only applies to movement in a local area, so if the local area is moving, you're okay. Let's just go with the fact that it's much easier to call than to visit in person. It's significantly easier and cheaper to send out light or radio waves, as simple as turning on a sufficiently large light bulb. So, let's assume that this is how our first contact with aliens will occur. Even here, however, we hit a roadblock. Radio signals and light are more than capable of traveling at relativistic speeds. It's called the speed of light for a reason, after all. However, that's its limit. Light speed. Just under 300 million meters per second. No signal can go faster than that. And this, in turn, limits how far we are able to see through space. Any signal from us would need to travel out across space before reaching alien life. And then, even if they decide to respond immediately, their response would need to travel all the way back. If they decided to respond. Let's imagine that happens though. We only invented the radio in the mid-1890s, so we have not really been able to do this for very long. As such, we would only be able to exchange a message with aliens who lived at most 60 light years away from us. 60 years for a signal sent out in 1900 to reach the alien civilization, and 60 years for it to come back. Our galaxy is roughly 100,000 light years across. Every photo taken during the Apollo missions shows a sky utterly empty of stars. Despite the universe being filled with trillions of stars, Apollo astronauts reported that they couldn't see a single star from the moon. This absence of stars has sparked conspiracy theories for years. Some even claim it's proof that the moon landing was a hoax. But the real explanation is far more fascinating and dives deeper than any conspiracy theory could. Why is space so black? This question was first purposed by Johannes Kepler back in 1610. Our Milky Way galaxy alone is estimated to contain anywhere from 100 to 400 billion stars, and the observable universe is estimated to contain 100 to 200 billion galaxies. By this notion, astronomers wondered that since the universe is filled with an endless number of celestial objects in all directions, couldn't every patch of the sky be uniformly bright and filled with light? Surprisingly, it's not, and this puzzled astronomers for centuries. Careful analysis suggests that the sky should be as bright as the surface of the sun. Yet, when we look up at night, we see mostly darkness. This paradox, known as Olbers Paradox, took nearly 300 years to resolve. The paradox of Olbers had emerged from the steady state theory. Imagine a universe where everything has always been the same and always will be. The stars, the galaxies, all of it, unchanged forever. This is the core idea behind the steady state theory, which was once the leading explanation of the universe. It proposed that the universe was infinite, without a beginning or end, uniform in every direction, and importantly, it did not expand. With this theory in mind, astronomers faced a question: why is the night sky dark? If the universe has always existed and is filled with stars, then shouldn't all of the night sky be as bright as the sun? According to the steady state theory, even the light from the most distant stars should have reached us by now, lighting up the sky with their collective glow. One early explanation suggested maybe the stars were just too far away to affect our night sky, but this idea didn't hold up under the steady-state model. The age of the universe is infinite, giving plenty of time for the light from any star, no matter how distant, to travel to Earth. This light should fill the sky, leaving no dark patches behind. Johannes Kepler had a different idea to solve the paradox, and it went against the popular theory of his time. He suggested that the universe wasn't infinite after all. Instead, he proposed that the stars only spread out to a certain limit, and beyond that, there was just empty space. This idea was intriguing, but it raised some big questions. How far does this space with stars go? And what's beyond that edge? Kepler's idea of a universe with limits also came with its own set of problems. If the universe had a boundary, the combined gravity of all the stars and planets could potentially pull everything back together, leading to a collapse of the universe. Because of these challenges, most astronomers kept believing that the universe was infinite. This meant that the paradox and the idea of a steady universe were left unresolved and forgotten for nearly 200 years. Then, a famous German astronomer named Heinrich Wilhelm Olbers brought attention back to this old question, asking again, why is the night sky dark? Since then, Olbers' name has become closely linked with the paradox. In his time, people still believed that the universe was unchanging, endlessly old, and infinitely large. Olbers proposed a straightforward idea. If the universe is infinite, then it makes sense that there would be endless amounts of dust and rocks in it. These particles could block the light from distant stars, causing them to look dimmer from our perspective. This dust and rocks in space absorb and block starlight as they move through the cosmos. Today, many people still believe this theory, comparing it to how clouds can block sunlight and obscure our view of the sky. Just like clouds, cosmic dust and rocks can hide the light from stars. However, Olbers' explanation wasn't a complete solution. Over time, the dust and rocks that block the light would heat up and start to glow themselves. This means the universe would still be filled with light, just like before. The dust and rocks just temporarily hide the light from the stars before releasing it again. So, the overall amount of light reaching us would still be the same. So, what really solves this paradox? It took another 100 years to find the real answer to the paradox. In 1929, Edwin Hubble used his powerful telescope, hoping to find signs of the universe shrinking. This would support the idea of a finite universe, just like Kepler had suggested. But instead, Hubble was surprised to find that the universe was not collapsing. Rather, he saw that galaxies were moving away from us, and the farther a galaxy was, the faster it seemed to be moving away. This showed that the universe was not staying the same or collapsing, but was actually expanding. This discovery led to a new question. What does an expanding universe mean for its beginning? Scientists now think that the universe started as something incredibly tiny and dense. It then expanded very quickly, a process called cosmic inflation. As it expanded, it cooled down, and eventually, stars and galaxies began to form. This understanding helped develop what we now call the Big Bang theory. Scientists believe this all started about 13.8 billion years ago, and it's currently our best explanation of how our universe was born. Today, most scientists agree that the universe is about 13.8 billion years old. When we look at light, that's 13.8 billion years old. We don't see stars, not because the light hasn't reached us, but because we are looking back to a time before stars even existed, a time when the universe had no stars at all. The farther we look into space, the further back in time we are seeing, until we reach what seems like the edge of the universe. This isn't a real edge, but rather the oldest light we can see, known as the cosmic microwave background. It's the leftover glow from the Big Bang and marks the farthest point we can see from Earth. When we use telescopes to look beyond the earliest stars, we see a special type of light. This isn't light from stars, but light that's left over from the Big Bang. It forms a kind of background glow beyond where the stars are. However, the Big Bang theory brings up a new issue. It suggests that the universe used to be much brighter, especially during a time called the recombination era. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow from the Big Bang, known as cosmic background radiation, should be very bright. According to Olbers' paradox, this bright background should make it hard for us to see any faint stars in the night sky. Since the Big Bang happened 13.8 billion years ago, the universe has been following three main rules as it grows and changes. First, at the very beginning, the universe was extremely tiny, very dense, and super hot. Second, just a tiny fraction of a second after it started, the universe began to grow bigger and cooler. Third, and this is really important, the universe will keep expanding and cooling down. Astronomers believe this will go on until the universe becomes so cold that all heat disappears. They call this the heat death of the universe, sometimes also known as the Big Freeze. In this future scenario, the universe has expanded so much that it has cooled down completely and all heat energy has gone away. All these rules show us that our universe has been getting bigger for the last 13.8 billion years. When the universe started, it was filled with very bright and hot light. As the universe has expanded, this light has been stretched out. This stretching has turned the light into longer wavelengths, which means it's cooler and not as bright as before. This is what we call the red shift effect. It's the reason why the cosmic background radiation we see today isn't extremely bright and doesn't light up the sky like it used to. With the discovery of redshift and cosmic background radiation, we can now say with certainty that the solution to Olbers' paradox is the Big Bang and the expansion of the universe. The universe was born from a singularity and expanded rapidly during the Big Bang, cooling down over billions of years. The finite age of the universe means that there is a limit to how far we can see, and the redshift effect ensures that the light we observe from distant objects is faint, leading to the dark night sky we see today. Thanks to the discovery of redshift and cosmic background radiation, we now understand that the Big Bang and the expansion of the universe solve Olbers' paradox. The universe started from a single point and quickly grew during the Big Bang. Over billions of years, it has cooled down. Because the universe isn't infinitely old, there's a limit to how far we can see into space. The redshift effect also makes the light from faraway objects appear dimmer. These factors combine to give us the dark night sky we see today. The fact that the night sky is dark shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe started with the Big Bang and has been expanding ever since. The night sky is like a quiet reminder of how the universe began as a very hot and dense place and has grown into the huge, cool space we live in now. This insight helps solve Olbers' paradox and also makes us appreciate just how amazing and complex the universe really is. One of the central theories in modern cosmology, the Big Bang theory, suggests an idea of how our observable universe was born. It explains the origin and evolution of the universe. Imagine the entire universe, every star, planet, and galaxy packed into an incredibly hot and dense point. That's how scientists believe it all began, about 13.8 billion years ago. Since then, it has been expanding and cooling down. This tiny point exploded in an event we call the Big Bang, and from that moment, the universe started expanding and cooling. But how do we know this happened? The theory of the Big Bang is supported by a lot of evidence. One important piece is the cosmic microwave background radiation, which is an afterglow left over from the early universe. This radiation gives us a picture of the universe just 380,000 years after the Big Bang. Before that universe was so hot and dense that we weren't able to take pictures of the Big Bang itself. Another important discovery is the redshift of galaxies. This means that galaxies are moving away from us, which shows that the universe is expanding, doubling, and doubling in size, not slowing down. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it seems to be moving away from us. This supports the idea that the universe was once much smaller, hotter, and denser. The Big Bang theory also explains the amounts of light elements like hydrogen, helium, and lithium in the universe. These elements were formed in the first few minutes after the Big Bang, when the universe cooled enough for protons and neutrons to make nuclei. But the Big Bang theory also raises some big questions. For example, it doesn't explain what happened before the Big Bang and how the universe formed from nothing. When we look around, we see that everything is made of tiny particles. These particles have been coming together for billions of years, forming humans, planets, stars, and galaxies, all following the same physical rules and existing in the same space and time. But there was a time when there was nothing in the universe. So where did all this stuff come from? Scientists think about this in different ways. They consider the possibility that everything came from something, but also that it might have come from nothing. But what does nothing mean in science? From a scientific perspective, there are 4 different ways to think about nothing. Let's explore each one. Let's imagine a universe with nothing in it. No stars, planets, or anything else we see. Everything we know is made of tiny particles. These particles build up to create everything around us. Starting from a universe full of stuff, we can understand how it changed over time to become what we see now. Stars, for example, change over their lifetimes, making heavier elements that lead to new stars, planets, and even life. But there's a big question. Why is our universe mostly made of matter, not equal amounts of matter and antimatter? This is a huge mystery in physics. According to the rules of physics, matter and antimatter should be made in the same amounts. But when we look at the universe, we hardly see any antimatter. It's almost all matter. So, how did we end up with more matter than antimatter? Scientists call this puzzle baryogenesis. It's about how the universe got more baryons than antibaryons when it was young. Scientists have lots of ideas, but we still don't have a clear answer. We don't know why there's more matter than antimatter instead of an equal amount. Another way to think about nothing is as the vast emptiness of space. Imagine a scenario where there's absolutely nothing. No particles, no energy, just empty space stretching on forever. In this emptiness, some scientists see the true meaning of nothingness. But even in this completely empty space, there are still some fundamental things that remain. The laws of physics are still at work, like the forces that govern how things move and interact. There are also quantum fields, which are like invisible forces that exist everywhere. These include fields like gravity and electromagnetism. Even though there's no matter or energy, there's still something called zero-point energy, which is a tiny amount of energy present even in empty space. Today, we understand this as dark energy, which is causing the universe to expand. So, even in a universe where there's absolutely nothing, there's still something happening. This idea challenges our understanding of what nothing really means and shows that even emptiness can be a fascinating part of the universe. Scientists also consider nothing as the ultimate lowest energy state possible for space and time. Right now, our universe contains something called zero-point energy, a tiny amount of energy present everywhere in space. We're not sure if this zero-point energy is the lowest possible energy or if there's an even lower state we haven't discovered yet. There's a chance we might be in what's called a false vacuum state, where the true vacuum, or the absolute lowest energy state, is very close to zero or even at zero. If the universe were to switch from this false vacuum to a true vacuum, it could lead to a major event called vacuum decay. This would cause significant changes, like photons, particles of light, gaining mass, the electromagnetic force acting over shorter distances, and less sunlight reaching Earth. Thinking of nothingness as the ultimate lowest energy state means removing all matter, energy, radiation, and any distortions in space and time. What's left is perfect emptiness, but the laws of physics still apply. In this state, there would still be a backdrop for events to happen, but without any actors or actions. It's like a play with no characters, storyline, or setting, just an empty stage. This ultimate low energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space, time, and the laws of physics would still exist. Now, imagine reaching the universe's true foundational state, whatever that might be. In this state, all matter, energy, and any distortions in space-time would be removed. What would be left is the ultimate material emptiness. There would still be a backdrop for events to happen, but without any actors or actions. It's like a play with no characters, storyline, or setting, just an empty stage. This ultimate low energy state would make it impossible to create any work, energy, or particles from it. However, some might still see this as something because space, time, and the laws of physics would still exist. So, our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the framework of space, time, and the laws of physics remain. It's another incredible mystery that keeps scientists exploring and searching for answers. Our fourth take on nothing is the most extreme. It suggests that true nothingness only occurs when the entire universe and its laws vanish completely. This concept pushes the boundaries of our understanding of reality to the limit. Imagine eliminating everything, including space, time, and even the laws that govern physics. This type of nothingness surpasses what we can grasp with physics because it signifies an absolute void, a complete absence of everything. From a physics perspective, this idea poses a challenge. How can something like space-time exist if there's no space or time? How can the laws of physics operate without a framework for them? This form of nothing is difficult to grasp and may lack any real-world significance. Thinking about this ultimate nothingness brings up many questions without clear answers. For instance, how could space and time initiate in a realm where they don't exist? Is it conceivable to have something beyond the universe devoid of space, or something commencing without time? Envisioning absolute nothingness, a total void, presents a conundrum from a physics standpoint. It implies a state transcending the confines of space and time, from which our universe and its laws may have emerged. However, we're uncertain whether this notion holds any meaningful significance or is merely a construct of our imagination. This concept prompts many challenging inquiries. For example, how could space and time have a beginning in a place or moment where neither exists? Can we even conceive of something existing outside the universe without space or initiating without time? Where would the principles governing particles and their interactions originate? While the idea of nothingness appears philosophically comprehensive, it may lack tangible substance. It could merely serve as a tool for us to comprehend phenomena beyond our tangible reality. When scientists discuss nothing, they often assume everyone shares the same concept of what nothing entails. However, that's not always the case. Different individuals and varying contexts can alter our perception of nothing. The phrase, something from nothing, might imply the creation of entirely new things from a state of true emptiness. Yet, there's disagreement on what nothing truly represents. Ultimately, it's crucial to discern which version of nothing someone is referring to, as each holds its own boundaries and applications. However, all these notions remain influenced by our human comprehension. It's intriguing that everything we know appears to have originated from nothing. In 1972, an extraordinary spacecraft named Pioneer 10 embarked on an exciting mission to explore the asteroid belt and the massive gas giants in the outer reaches of our solar system. Traveling at a speed of 32,000 miles per hour, Pioneer 10 set off from Earth on a journey that would pave the way for future missions like the Voyager probes. Pioneer 10's mission was a remarkable success, but it wasn't without its challenges. Little did we know, the probe carried a hidden problem, a riddle that would puzzle scientists for decades. Nicknamed as the luckiest spacecraft ever launched, Pioneer 10 faced numerous malfunctions. In the early 1980s, while the probe was still communicating with Earth, scientists noticed something strange. Pioneer 10 was slowing down and veering off course, as if an unknown force was pulling it back towards the Sun. For about 15 years, researchers conducted extensive studies and analyzed data, but they couldn't solve the mystery. The unexplained slowdown eventually stopped, leaving behind one of the greatest enigmas in spaceflight history. This phenomenon, known as the Pioneer anomaly, remains unsolved. Even today, the flyby anomaly continues to puzzle scientists. This glitch challenges our understanding of spaceflight and keeps us searching for answers. The Pioneer anomaly is a reminder that, despite our advances in space exploration, there are still mysteries in the universe that test our knowledge and ignite our curiosity. Launched in 1972, Pioneer 10 was NASA's groundbreaking mission to explore the outer planets. The probe was named after the brave pioneers who settled the western United States, as it aimed to boldly go where no spacecraft had gone before. Pioneer 10 achieved remarkable milestones, including several firsts in space exploration. It was the first spacecraft to travel beyond Mars, cross the asteroid belt, and reach the gas giant Jupiter. Pioneer 10 also made history as the first spacecraft to use an all-nuclear power supply and follow a path that would take it beyond our solar system. Although it was originally intended for a 21-month mission, Pioneer 10 far exceeded expectations, operating for over 30 years. In January 2003, after a long and distant journey, the probe sent its final signal back to Earth. Today, Pioneer 10 continues its voyage, drifting like a ghost ship through the cold expanse of space, more than 11 billion miles away, moving in the opposite direction of the Sun's motion through the galaxy. Twin to Pioneer 10, Pioneer 11 launched a year later in 1973, embarking on its own journey into the great unknown. Like its predecessor, it became the second probe to pass Mars, navigate the asteroid belt, and reach the giant planet Jupiter. Pioneer 11 then made history as the first spacecraft to fly by Saturn. Unlike its twin, however, Pioneer 11 left Saturn on a different path, heading out of the solar system at a 90-degree angle to Pioneer 10, towards the center of the galaxy, in the direction of the constellation Sagittarius. In 1995, NASA received the last signal from Pioneer 11, marking the end of its communication. It silently vanished into the depths of space, leaving behind a legacy of exploration. But both Pioneer 10 and 11 left behind a puzzle that would baffle physicists for decades. Shortly after Pioneer 10 and 11 ventured beyond the orbits of Jupiter and Saturn, their navigators noticed something strange. Both spacecraft were slowing down more than expected, as if an unknown force was gently pulling them back towards the sun. While some deceleration due to the sun's gravity was anticipated, the data showed an excessive slowdown that couldn't be easily explained. The deceleration was incredibly small, just 1/10,000,000th of Earth's gravitational acceleration. In 1998, John Anderson of JPL and his colleagues calculated that the spacecraft were decelerating at a rate of about 300 inches per day. While this difference seemed tiny, it had significant implications. The pioneers ended up thousands of kilometers closer to Earth each year than expected, eventually falling short of their predicted locations by distances similar to the gap between Earth and the Moon. Year after year, the spacecraft deviated by a few thousand kilometers from their expected positions. Initially, this didn't raise many concerns, but as time passed, it became clear that this tiny deceleration persisted as the spacecraft traveled deeper into space. The Pioneer anomaly remains one of the greatest mysteries in space exploration, challenging our understanding and sparking curiosity about the forces at play in the cosmos. This mystery adds to the many questions we have about the universe, pushing us to seek answers and explore further. As we dive deeper into the mysteries of the universe, we find that everything we see, like stars and galaxies, is made of matter. Matter makes up about 5% of the universe and includes all the atoms and particles of the universe. Next, we have dark matter, which accounts for about 27% of the universe. We can't see dark matter, but we know it's there because of its gravitational effects on visible matter. It's like an invisible framework that helps shape and form galaxies. The biggest and most puzzling component is dark energy, making up about 68% of the universe. This mysterious force is causing the universe to expand faster. Together, matter, and dark energy create the fabric of the universe, from the tiniest particles to the largest galactic structures. While we don't fully understand what dark matter and dark energy are, we are fairly confident they exist. Here's what we know. Dark matter is crucial for galaxies to form. When scientists studied the structure of the universe, they realized there wasn't enough regular matter to explain how galaxies and complex systems are created. The gravitational pull of visible matter alone isn't strong enough to form galaxies. Without dark matter, stars would probably be scattered randomly instead of forming the beautiful galaxies we see. This suggests that dark matter acts like a glue, holding galaxies together. Dark matter is a mysterious component that neither emits nor reflects light, making it invisible. However, we can indirectly observe dark matter through a phenomenon known as gravitational lensing. Areas with high concentrations of dark matter bend light that passes close by, acting as a clue and revealing its presence through gravitational interactions. We know that dark matter isn't just ordinary matter without stars. Ordinary matter emits detectable particles, making it visible to our instruments. If dark matter were simply ordinary matter, we would have already observed it. This tells us that dark matter is something different, adding to the mystery and driving further research. Dark matter also isn't antimatter. Antimatter emits unique gamma rays when it reacts with regular matter. If dark matter were antimatter, we would detect these gamma rays, but we haven't. Additionally, dark matter isn't made up of black holes. Black holes are dense objects that dramatically affect their surroundings, while dark matter appears to be spread out across the universe. The gravitational effects of black holes differ from what we observe with dark matter. Scientists are exploring various hypotheses and conducting experiments to uncover the true nature of dark matter. Despite the mystery, these efforts continue to bring us closer to understanding this elusive substance. Even the ultra-precise 15-month survey of the cosmos by the European Space Agency's Planck spacecraft was only able to detect less than 5% of the total of the observable universe. For years, scientists have been trying to solve the mystery of dark matter. They have been able to infer the existence of dark matter only from the gravitational effect it seems to have on visible matter. Renowned British physicist Brian Cox explains about dark matter and considers it as some kind of particle that we are currently unknown. Dark energy is even more mysterious than dark matter. We can't directly detect or measure it, but we can see its effects. In 1929, astronomer Edwin Hubble made a groundbreaking discovery. He studied how light from distant galaxies shifts towards the red end of the spectrum as it travels through space. This phenomenon, known as redshift, revealed an astonishing truth. Hubble found that more distant galaxies showed more redshift, while closer ones showed less. He concluded that this redshift was due to the universe expanding. As light wavelengths stretch, they shift towards the red end of the spectrum, indicating that space itself is growing. Recent discoveries have taken this even further. The universe's expansion is not just continuing, it's accelerating. Previously, scientists believed that gravity would slow down or even reverse this expansion, but dark energy is driving it to speed up. Scientists have discovered that the rapid expansion of the universe is due to dark energy. This mysterious force is driving the universe apart at an ever-increasing rate. As the universe expands, space itself doesn't change its properties. There's simply more of it. New space is constantly being created everywhere. Galaxies remain tightly bound clusters held together by gravity, so we don't experience this expansion in our daily lives. However, we can observe it throughout the universe. Wherever there's empty space, more is forming every second. These discoveries about dark energy continue to challenge and expand our understanding of the cosmos. So, what is dark energy? It appears to be a type of energy intrinsic to empty space, stronger than anything else we know, and constantly increasing. Empty space holds more energy than everything else in the universe combined. This mysterious force is pushing galaxies apart and accelerating the expansion of the universe. Dark energy remains one of the greatest mysteries in cosmology. While we can't detect or measure it directly, its influence on the universe is undeniable. The discovery that the expansion of the universe is speeding up suggests that dark energy is at work. Understanding dark energy is one of the biggest challenges in cosmology today. As we continue to explore and study the cosmos, we hope to unravel the secrets of this enigmatic force, bringing us closer to understanding the true nature of our ever-expanding universe.
One of the most famous features in our solar system is the Great Red Spot on Jupiter. This huge storm, larger than Earth, has been active for at least 400 years, and maybe even longer. The Great Red Spot is a massive swirling storm that has caught the attention of scientists ever since it was first seen. But what exactly is this storm, and why has it lasted for so long? The Great Red Spot is a high-pressure area in Jupiter's atmosphere, creating a storm that spins counterclockwise in the planet's southern hemisphere. The storm is so big that it can be seen from Earth through telescopes. In fact, it's about 1.3 times the size of Earth. The edges of the storm spin faster than the center. One of the biggest questions about the Great Red Spot is its reddish color. Scientists aren't entirely sure why it's red. Some ideas suggest that chemicals in Jupiter's atmosphere, like phosphorus or sulfur, might be causing the color when they react to sunlight. Another idea is that chemicals from deeper in the storm might be getting pushed to the surface. Whatever the reason, the red color makes the storm stand out among Jupiter's bands of white, brown, and yellow. Another fact is that the Great Red Spot has lasted for so long. On Earth, storms usually only last a few days or weeks, but the Great Red Spot has been around for centuries. This is partly because of Jupiter's unique atmosphere. Jupiter is a gas giant, meaning it doesn't have a solid surface like Earth. Since there's no land to slow it down, the storm can keep going. Also, Jupiter's large size and fast spinning help the storm stay active. Jupiter's quick rotation plays a big part in keeping the Great Red Spot going. Jupiter spins much faster than Earth, completing one full turn in just under 10 hours. This fast spinning creates strong winds, called jet streams, that help hold the storm in place. These winds act like walls, keeping the storm in its area and stopping it from fading away. The way these winds interact with the storm helps keep it going strong. Even though the Great Red Spot has been around for a long time, it won't last forever. Over the past few decades, scientists have noticed that the storm is slowly shrinking. Back in the 1800s, the storm was about 25,000 miles wide. Now it's less than half that size. Scientists are studying this change to understand why it's happening and what it might mean for the storm's future. The exact reasons for the shrinkage aren't fully known yet, but it could have to do with changes in Jupiter's atmosphere or interactions with other storms. The wind inside the Great Red Spot is incredibly strong, reaching speeds of up to 400 miles per hour. These winds create tall clouds that rise high above the surrounding atmosphere. The storm on Jupiter, known as the Great Red Spot, has a layered structure with different temperatures and wind speeds at different heights. These layers help scientists learn more about how the storm works and how it affects Jupiter's atmosphere. The top of the Great Red Spot is much cooler than the clouds around it, which shows that the storm goes deep into Jupiter's atmosphere. In recent years, NASA's Juno spacecraft has given us a closer look at the Great Red Spot. Juno, which has been orbiting Jupiter since 2016, is packed with tools to study the planet's atmosphere, magnetic field, and inner structure. Juno's close passes over the Great Red Spot have revealed that the storm reaches much deeper into Jupiter's atmosphere than we thought, possibly hundreds of miles deep. This shows that the Great Red Spot is a massive structure with strong roots deep inside Jupiter's thick atmosphere. The Great Red Spot also helps us understand atmospheres on other planets, even ones outside our solar system called exoplanets. By studying this giant storm, scientists can create models to predict weather on other gas giants and even potentially habitable planets. This information helps us learn more about how atmospheres work not just in our solar system but across the universe. The Great Red Spot is a mystery that continues to inspire us. It reminds us of the powerful forces at work in our solar system. Every new discovery about the storm helps us get closer to understanding it, but also shows how much more there is to learn about Jupiter and other giant planets. This storm has lasted for centuries and continues to change, making it a perfect place to study how atmospheres behave under extreme conditions. Beyond science, the Great Red Spot has become a cultural symbol. It has appeared in many works of science fiction, art, and literature, representing the unknown wonders of our solar system. Its striking appearance makes it a favorite subject for both professional astronomers and amateur stargazers. Looking at the Great Red Spot through a telescope is a thrilling way to connect with the vast universe beyond Earth. Studying the Great Red Spot also helps us appreciate the balance of Earth's atmosphere. While Earth's storms are much smaller and don't last nearly as long, they work in a similar way. The future of the Great Red Spot is uncertain. Will it keep shrinking until it disappears, or will it find a way to stick around for many more centuries? Scientists are eager to know, and missions like Juno will help answer these questions. The information gathered by Juno and other future missions will help scientists make better models of Jupiter's atmosphere and understand how its most famous storm will behave in the years to come. Nothingness, an absolute void, is a concept that challenges the human mind. We often assume that everything must come from something, but how did everything begin? We sometimes claim it started from nothing, but how can nothing become something? In the vastness of the cosmos, where galaxies shine and black holes pull in matter, the idea of nothingness stretches our understanding of the universe. This isn't just a philosophical question, it's a core idea in cosmology that has intrigued scientists and thinkers for centuries. Imagine a region of space completely free of stars, planets, or any form of matter. a quiet stretch of the universe where the usual rules of physics may no longer apply. Though it seems contradictory, nothingness plays an essential role in our understanding of the universe. To grasp the mysteries of the cosmos, we must first understand what nothing means in the context of space. At first glance, the emptiness of space might seem like a perfect vacuum with no matter or energy. While there is some truth to this idea, it doesn't capture the full picture that modern science has revealed. In today's understanding, nothingness is not an empty void, but a dynamic space filled with unexpected activity. Let's dive into this idea through the lens of science. Contrary to what we might think, space is not truly empty. It is alive with quantum fluctuations, where particles and antiparticles briefly pop into existence, only to cancel each other out. This gives the vacuum a constantly changing nature. Even in areas with no visible matter, space is linked to the fabric of space-time, as described by Einstein's theory of general relativity. Massive objects, like stars or black holes, can still bend space-time, affecting how things move around them. When we peer into the depths of space, we can detect the faint afterglow of the Big Bang, the cosmic microwave background radiation. This relic from the early universe reminds us that space has changed over time. Yet, despite our progress, the idea of nothingness remains a deep puzzle, one that both scientists and philosophers continue to ponder. Some theories suggest that there might be parts of the universe where the density of matter is incredibly low, close to absolute nothingness. While these ideas remain largely speculative, they point to the possibility of vast voids in space. If such regions exist, they could help us better understand the true nature of space. Is empty space really devoid of all matter and energy? This question, which seems simple on the surface, leads to a wealth of scientific and philosophical inquiry. Traditionally, we think of space as an empty vacuum, a blank canvas without matter or energy. This fits with our basic idea of emptiness, but the deeper we go into the study of the universe, the more we find that reality is far more complex than we once thought. In quantum mechanics, which explains the behavior of particles at the smallest scales, we encounter another challenge to our idea of nothingness: quantum fluctuations. These suggest that even in the emptiest parts of space, particles and antiparticles can appear, briefly interact, and then vanish again. These momentary events give the void a kind of restless energy, challenging our understanding of what it means for something to be truly empty. Additionally, Einstein's theory of general relativity shows us that space and time are woven together into a four-dimensional fabric called spacetime. Massive objects like planets or stars can bend this fabric, pulling nearby objects toward them. So the idea of a completely empty, untouched space becomes harder to imagine. How does the idea of nothing connect with dark matter, and what does it reveal about the universe's structure? To answer this, we first need to understand dark matter itself. Unlike the ordinary matter that makes up stars, planets, and galaxies, dark matter remains invisible, only making itself known through the gravitational forces it exerts. It represents the ultimate form of nothingness, as it escapes direct observation and doesn't fit traditional definitions of matter. Dark matter's existence was suggested by observing galaxies and their movements. The gravitational pull from visible matter alone couldn't explain their behavior. To account for this gap, scientists proposed the presence of an unseen, intangible substance, dark matter, that fills cosmic spaces and holds galaxies together. The Big Bang theory suggests that the universe began about 13.8 billion years ago, starting from a singularity, a point of infinite density and temperature. This moment marked the birth of space and time itself, emerging from what might seem like nothing in conventional terms. But how does this explosive start connect with the idea of nothingness? To understand, we must look closer at the nature of the singularity. A singularity represents a state where the normal laws of physics don't apply, a point with infinite density and zero volume, defying our usual ideas of matter and space. In this way, the singularity reflects a form of nothingness, where the universe lacked the familiar structure and dimensions we recognize. However, this nothingness was packed with potential. As the universe expanded from this singularity, it went through a rapid phase of inflation, causing space to stretch almost instantly. This expansion transformed the universe from a state of near-nothingness into a space filled with energy, particles, and forces that shape the cosmos as we know it. In the early moments after the Big Bang, the universe was extremely hot and dense, like a thick soup of particles and radiation. In less than a second, it underwent a series of changes, including nucleosynthesis, where the first atomic nuclei came together. This evolution paved the way for stars, galaxies, and the intricate structure of the universe we see today. How do we know the Big Bang happened? There is plenty of evidence supporting this idea. One key clue is the cosmic microwave background radiation, a faint afterglow left over from the early universe. This radiation gives us a picture of the universe as it looked about 380,000 years after the Big Bang, when it finally cooled enough for light to travel through space. In 1965, Arno Penzias and Robert Wilson found this radiation by accident, providing strong support for the Big Bang theory. The even spread of the CMB and its small variations support the idea of cosmic inflation, a period of rapid expansion in the early universe. Another key piece of evidence is the redshift of galaxies. This redshift shows that galaxies are moving away from us, indicating that the universe is expanding. In the 1920s, Edwin Hubble first observed this, and he noticed that the farther away a galaxy is, the faster it moves away, backing up the idea that the universe started small, hot, and dense. However, the Big Bang theory leaves some major questions unanswered. For instance, it doesn't explain what came before the Big Bang or what lies beyond the edge of the observable universe. It also introduces the idea of cosmic inflation, a phase of rapid growth right after the Big Bang, which still puzzles scientists. Before the discovery of the cosmic microwave background radiation, there was another popular theory called the steady-state theory. This theory suggested that the universe has no beginning or end, but stays the same overall, even though it expands, by constantly forming new matter. This idea was well known in the 1940s, but lost support after the CMB radiation was found in 1965, giving strong backing to the Big Bang theory. There are also other ideas, like the cyclic model, which suggests that the universe goes through endless cycles of expansion and shrinking. After the Big Bang, the universe kept expanding and cooling. In the beginning, it was a hot, dense mix of particles. As it spread out, it cooled, allowing particles to join together and form the first atoms. These atoms eventually formed the first stars and galaxies, and the universe's expansion continues today, with galaxies moving away from us in all directions. Going back to the earliest moments of the universe, the first long-lasting particles were protons and neutrons, which formed the nucleus of atoms. These particles appeared around 1/10,000th of a second after the Big Bang. Before this, there was no material in the way we understand it. However, physics allows us to trace the timeline even further back to events that occurred before stable matter existed. To grasp how the universe could begin from nothing, we need to explore the strange world of quantum mechanics. In quantum physics, nothing isn't an empty void, but rather a state of vacuum energy, where particles constantly appear and vanish. This is known as quantum fluctuations. Quantum fluctuations happen in a state called the quantum vacuum, which has the lowest possible energy level. In this state, particles can momentarily come into being and then disappear. According to quantum mechanics, these fluctuations can, in theory, lead to the creation of a universe. So, in this context, nothing is an energetic state that has the potential to bring matter and energy into existence. A key idea here is Heisenberg's uncertainty principle. This principle states that certain pairs of physical properties, like position and momentum, cannot both be measured with complete accuracy at the same time. This principle allows particles to briefly pop into existence from the vacuum as long as they disappear quickly enough to respect the law of conservation of energy. These quantum fluctuations cause particles to appear and vanish shortly afterward. While this might sound strange, such particles have been observed in many scientific experiments. The vacuum of space is filled with particles constantly being created and destroyed, suggesting that the quantum vacuum is not truly empty. But where did space-time itself come from? To answer this, we need to look back to the very beginning of the universe into a period called the Planck epoch. This phase occurred so early in the universe's history that our current theories of physics stopped working. It happened only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Usually, scientists rely on quantum mechanics to explain tiny particles and on general relativity to explain the large-scale structure of the universe. But to understand the Planck epoch, we need a theory that combines both, something known as quantum gravity. We don't have a complete theory of quantum gravity yet, but there are ideas like string theory and loop quantum gravity. These theories suggest that what we experience as space and time may come from deeper, microscopic processes. The space and time we're familiar with are the result of these quantum processes, which are difficult for us to understand because we live in a world of large-scale objects. Quantum fluctuations occur constantly, even in what we consider to be empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can appear from the vacuum, exist for a brief moment, and then cancel each other out. This process is sometimes called quantum foam. However, quantum fluctuations alone don't explain the vast scale and complexity of the universe. There is also dark energy, a mysterious force that fills all of space and speeds up the expansion of the universe. While we don't fully understand dark energy, it seems to play a key role in the creation and growth of the cosmos. So, how did we get from quantum fluctuations and dark energy to the universe we see today, filled with galaxies, stars, and planets? The answer lies in inflation, a period of rapid expansion that took place fractions of a second after the Big Bang. During this brief time, the universe expanded at an incredible rate, setting the stage for the formation of everything we observe today. In the Planck epoch, our normal understanding of space, time, and cause and effect breaks down. Despite this, all the leading theories of quantum gravity suggest that something physical was happening during this period, some quantum process that led to the space and time we know. But where did this come from? That remains one of the universe's most profound questions. Even though causality might not function in the way we typically understand, there is still hope that parts of the Planck epoch universe could explain other parts. Unfortunately, our current understanding of physics cannot yet provide clear answers. Until we develop a complete theory of everything, we won't be able to give a definite explanation. What we do know for certain is that no confirmed instance of something emerging from absolute nothing has been found. In this context, the idea of nothingness becomes more dynamic and complex. It is not a simple, empty void, but rather a canvas where the universe paints its story. A story that began with the explosive birth of the cosmos. One of the key questions in advanced cosmology is whether the vacuum of space is truly empty or whether it still contains particles or fields. At first glance, we might imagine space as a vast, empty expanse with no matter or energy. Yet, when we dive into the strange world of quantum mechanics, we discover something surprising. Space is not as empty as it might seem. Quantum mechanics, which explains how particles behave on the smallest scales, shows us that space is full of activity, even in what we think of as emptiness. The vacuum of space is not silent, it's alive with quantum fluctuations. These fluctuations are like tiny ripples on a calm pond, appearing at the subatomic level. In these fluctuations, particles and their opposites briefly appear, interact, and then disappear again, creating a fleeting dance of existence. These momentary events challenge our classical view of emptiness, revealing that the vacuum is constantly shifting and changing. In addition, the vacuum of space is not just an empty background, but plays an essential role in the universe. It hosts fields that control the fundamental forces, such as the electromagnetic field. These fields stretch across space, even in regions we think of as empty. In advanced cosmology, we learn that the vacuum is far from a simple void. It is a lively space, filled with quantum fluctuations and fields, blurring the line between nothing and something, and forcing us to rethink what emptiness really means. This idea also has real-world implications. Scientists have found ways to use the energy within these quantum fluctuations in a phenomenon called the Casimir effect. When two parallel conducting plates are placed very close together in a vacuum, they experience a small but measurable attraction due to the changes in the quantum fluctuations between them. This effect, though tiny, shows that the concept of nothingness in space can have real and measurable consequences. To truly answer how something could arise from nothing, we first need to explore several different interpretations of nothing. This interpretation describes a state where the essential building blocks of everything we see are absent. Imagine a universe without galaxies, stars, planets, or humans. Everything we interact with is made up of tiny subatomic particles, the fundamental components that shape the universe. Starting with a universe full of matter, we understand how it grows, cools, and becomes influenced by gravity, eventually forming the universe we know today. Stars live through cycles, creating heavier elements that lead to new stars, planets, and life. But one of the biggest questions in science remains: how did we end up with a universe dominated by matter, rather than equal amounts of matter and antimatter? This is one of the great unsolved mysteries in physics. The universe is almost entirely made of matter, with hardly any antimatter. So, how did we end up with this imbalance of matter? This puzzle is called baryogenesis, the process that created more baryons than antibaryons in the early universe. While there are many theories, we still don't have a clear answer as to why matter dominates over antimatter. Our second interpretation considers nothing as the emptiness of vast space. If you think of nothing as having no things at all, then the first interpretation, where particles are just missing, doesn't fully capture this idea. To understand this concept of nothingness, we need to imagine removing every single particle and all energy from space. If we manage to strip away all matter and energy, what remains is the empty expanse of space. No particles, no matter, no radiation. This is what some scientists regard as true nothingness. However, space-time itself, shaped by general relativity, still exists. The speed of light and the gravitational constant remain the same. There is also something called zero-point energy. Even in the most empty space, a small amount of energy remains. Today, we associate this with dark energy, which causes the universe to expand. But even in this extremely empty scenario, some fundamental elements remain. The laws of physics still exist. Quantum fields, such as the electromagnetic field, gravitational field, and Higgs field, are still present. So, even without matter or radiation, this version of nothing still gives rise to an intriguing universe. It's fascinating to realize that even in the absence of all the things we can see, the universe remains a lively and dynamic place. The third interpretation of nothing considers it as the lowest energy state possible. Right now, our universe has what's known as zero-point energy, a small amount of energy that exists everywhere in space. We don't know if this zero-point energy represents the absolute lowest energy possible, or if there could be an even lower energy state waiting to be discovered. We might be living in a false vacuum, with the true vacuum, the absolute lowest energy state, still out there. If the universe shifted from this false vacuum to a true vacuum, it could trigger a catastrophic event known as vacuum decay. This would fundamentally change the universe. Light particles would gain mass, the electromagnetic force would become limited to short distances, and most of the sunlight would no longer reach Earth. Thinking of nothing as the ultimate lowest energy state means imagining a scenario where all matter, energy, radiation, and any warping of space-time have been removed. What remains is a state of pure emptiness, though the laws of physics would still be present. In this state, it would be impossible to create work, energy, or particles. However, some would argue this still isn't truly nothing because space-time and the rules of physics still exist. It would be like a stage with no actors or plot, just an empty backdrop. So, our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the structure of space, time, and the laws of physics remain intact. It's another incredible mystery that keeps scientists searching for answers. Fourth interpretation of nothing. This is the most extreme interpretation of nothing. It suggests that true nothingness only happens when the entire universe and the rules that govern it completely disappear. This idea goes beyond anything we usually understand. Imagine removing everything, including space, time, and even the laws of physics. This kind of nothing cannot be defined by the rules of physics because it represents an absolute void, a total absence of everything. From a scientific perspective, this concept is hard to grasp. How could space-time exist without space or time? How could the laws of physics operate without a structure for them? This version of nothing is difficult to imagine and may not have any real-world meaning. Thinking about this kind of nothingness raises many questions without clear answers. For instance, how could space and time begin from a state where they don't exist? Is it possible to have something without space or start without time? Picture an absolute void known as a complete nothingness. From a physics viewpoint, it hints at a state beyond space and time from which the universe and its rules might have emerged. However, it's unclear if this idea is meaningful or just a product of our imagination. This concept introduces difficult questions. How could space and time begin in a place where neither exists? Could something exist outside the universe or start without time? Where would the rules that control particles and their interactions come from? While this idea of nothingness seems complete, it may not have any real substance. It might simply be a way for us to think about things that are beyond our experience. When scientists talk about nothing, they often assume that everyone shares the same idea of what it means. But that's not always the case. Different people and contexts can shape how we understand nothing. While theories about nothing are grounded in scientific studies, the study of the cosmic microwave background radiation or the faint afterglow of the Big Bang provides key insights into the conditions of the early universe. Precise measurements of the CMB have given us a better understanding of the age, makeup, and structure of the universe. Observations of the expanding universe, as described by Hubble's law, support the idea that the universe began from a hot, dense state. The discovery of dark matter and dark energy, which make up most of the universe's mass and energy, also shows that our understanding of the universe is still incomplete. The phrase "something from nothing" might refer to creating something entirely new where there was truly nothing before. But not everyone agrees on what nothing really means. So, it's important to clarify which version of nothing is being discussed. Black holes are among the strangest objects in the universe. They are regions where matter has been compressed to such an extreme degree that the gravitational pull becomes so strong that not even light can escape. Black holes are often thought of as ultimate voids, giving a new dimension to the concept of nothingness. At the heart of a black hole lies a singularity where density becomes infinitely high and the rules of physics as we know them no longer apply. This singularity can be seen as a counterpart to the nothingness that may have existed before the Big Bang. While black holes form from the remains of massive stars, the absence of matter within them and their powerful gravitational fields make them fascinating subjects when considering the universe's formation from nothing. Black holes form when massive stars use up their nuclear fuel and collapse under their own gravity. This collapse leads to a supernova, leaving behind a dense core that can become a black hole. Black holes play a significant role in the evolution of galaxies and the broader cosmos. They are often found at the centers of galaxies, including our own Milky Way, where they influence the motion of stars and gas. Supermassive black holes, with masses millions or even billions of times greater than the Sun, shape the dynamics of their host galaxies. The interactions between black holes and their surroundings provide important insights into the formation of cosmic structures, helping us understand how the universe evolved from a state of apparent nothingness. The idea of nothingness has been a subject of philosophical thought for centuries. Philosophers have long debated the nature of existence and the possibility of a state without anything. In cosmology, nothingness refers not only to the absence of matter, but to a state where space and time themselves do not exist. This idea challenges our everyday experiences and pushes the boundaries of human understanding. Some philosophical viewpoints argue that nothingness is impossible, as the concept itself suggests the potential for something to exist. Others suggest that the universe's emergence from nothingness highlights the complexity of reality, where even the absence of things can lead to everything we observe. Science also explores nothingness, often intersecting with philosophical ideas, particularly when discussing the origins of the universe. In physics, nothingness can be described as a quantum vacuum where particles and antiparticles appear and disappear constantly. This dynamic vacuum challenges the traditional idea of an empty void, suggesting that even space is full of potential activity. Theories like quantum field theory and quantum mechanics describe the probabilistic nature of particles and their interactions. The possibility that the universe could emerge from a quantum vacuum supports the idea that nothingness is not a static state, but one filled with potential for creation and transformation. The implications of nothingness reach beyond theoretical physics and cosmology. Understanding how the universe might emerge from nothingness can change our views on existence, creation, and reality itself. It challenges the conventional distinction between something and nothing, showing that the potential for existence may be embedded in the very nature of reality. This realization can also have profound philosophical and existential effects, influencing how we see our place in the universe and what existence means. Additionally, studying how the universe began from nothingness can drive new discoveries and innovations as we continue to unravel the mysteries of the cosmos and our beginnings. The concept of nothing has changed significantly over time, reflecting advances in both scientific and philosophical thought. In ancient times, nothingness was often associated with a complete void, without matter, energy, or space. However, as our knowledge of the universe grew, the idea of nothingness became more complex. Quantum mechanics introduced the idea that even in a vacuum, particles and antiparticles could appear and disappear, showing that nothing is not truly empty. This new understanding has important implications for how we think about the origins of the universe, emphasizing the dynamic nature of what we once considered a static void. As we explore the universe, our understanding of nothingness continues to evolve. The discovery that the universe is expanding, made by Edwin Hubble in the 1920s, revolutionized cosmology. This finding suggested that the universe had a beginning, which emerged from a singularity. This led to the development of the Big Bang theory, which describes how the universe began as a hot, dense point and has been expanding ever since. This theory suggests that before the Big Bang, there was a state of nothingness from which everything emerged. The idea that the universe could come from a quantum vacuum challenged traditional views and opened new paths for understanding the nature of reality. Revolutionary insights into nothingness have come from various areas of science, especially quantum mechanics and cosmology. One key idea is quantum fluctuations, which occur even in a perfect vacuum. These fluctuations cause temporary changes in energy that create particles and antiparticles, providing a possible explanation for how the universe could emerge from nothing. Additionally, the concept of cosmic inflation, a rapid expansion that took place right after the Big Bang, helps explain how quantum fluctuations may have grown into large-scale structures like galaxies. These insights have reshaped our understanding of nothingness, showing that it may be the starting point for the universe itself. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided key evidence for the Big Bang theory. The CMB is the faint afterglow of the Big Bang, filling the universe and giving us a glimpse of the cosmos about 380,000 years after its beginning. The uniformity of the CMB, along with its tiny temperature variations, reveals the early structure of the universe, supporting the idea that it started from a hot, dense state and expanded over time. This discovery was crucial in confirming the Big Bang model and advancing our understanding of how the universe could arise from a state close to nothingness. The concept of nothing is inherently puzzling, as we tend to think in terms of things that exist or don't exist. The idea of nothingness challenges the way we normally understand reality, forcing us to explore the limits of our thinking. In cosmology, this puzzle is seen in the idea that the universe could emerge from a quantum vacuum, a state that is not truly empty but filled with potential. The difficulty lies in reconciling the presence of the universe with the idea of a prior state of nothingness. This tension drives both scientific inquiry and philosophical debate, pushing us to refine our ideas and expand our knowledge. Quantum fluctuations in the vacuum offer an intriguing view of how the universe might have emerged from nothing. In quantum field theory, even in what seems to be a perfect vacuum, particles and antiparticles constantly appear and disappear due to energy fluctuations. These fluctuations are not random. They follow the principles of quantum mechanics, which allow for temporary shifts in energy. This active vacuum can give rise to a range of phenomena, including the formation of the universe. During the universe's early moments, these fluctuations were amplified by a period of rapid inflation, leading to the creation of matter and energy from what was once considered empty space. This process shows that what we think of as nothing is actually a dynamic space full of quantum activity capable of bringing the universe into being. Philosophically, nothingness has long been a subject of deep thought and debate. The idea challenges our basic understanding of existence and reality. In classical philosophy, nothingness was often seen as an absolute void, lacking matter, space, and time. However, modern physics has complicated this view by suggesting that nothingness may not be truly empty, but instead full of quantum potential. This shift challenges our understanding of what it means for something to exist, implying that even when matter and energy are absent, the universe still has the potential for creation. These reflections encourage us to rethink the nature of reality and the limits of our knowledge. Human senses are naturally limited when it comes to perceiving nothingness. Our senses detect matter and energy, such as light, sound, and heat. The concept of nothingness in physics often goes beyond what we can directly experience. For example, quantum fluctuations and the cosmic vacuum cannot be sensed directly but are inferred through advanced instruments and mathematical models. This gap between our intuitive understanding and scientific reality highlights the need for sophisticated tools and abstract thinking to understand concepts that lie beyond our everyday experience. Quantum phenomena present significant challenges to our understanding of nothingness. Quantum mechanics reveals that particles can exist in more than one state at the same time and can interact across great distances. These phenomena defy classical ideas of cause and effect, making it difficult to grasp how the universe could begin from a state of nothingness. The idea that quantum fluctuations could lead to the creation of the universe requires us to align these phenomena with the idea of a vacuum. This complexity highlights the challenges of quantum mechanics and its role in shaping our understanding of the cosmos, pushing both science and philosophy to their limits. Cognition and abstract thinking play a key role in our efforts to understand nothingness and the origins of the universe. Human thought is well suited to dealing with concrete experiences, but struggles with abstract concepts like the emptiness from which the universe might have emerged. Theories about quantum fluctuations and nothingness require a high level of abstract thinking and mathematical reasoning. These tools allow us to create models and ideas that go beyond what we can directly observe. The development of theories in cosmology and quantum mechanics relies heavily on this kind of advanced thinking, reflecting the limits of our natural understanding and the need for intellectual tools to explore the origins of the universe. Back in the 4th century BCE, a Greek scholar named Archytas imagined reaching the edge of the universe and trying to extend his hand further. He believed that if there was nothing beyond, then the universe must be infinite. In the 16th century, Italian philosopher Giordano Bruno also thought the universe was infinite, filled with countless stars and planets. In the 17th century, philosopher Thomas Hobbes took a more practical view. He believed that speculating about an infinite universe wasn't useful since we couldn't measure or observe it. He suggested focusing on what could be understood. This approach has shaped modern science, but despite the caution, some cosmologists still explore the question of the universe's infinity using today's technology and centuries of accumulated knowledge. When we look into space, it's like standing on an island, seeing only as far as the horizon. Light travels at a constant speed, so looking far into space is like looking back in time. We can observe galaxies as they existed 1 billion, 5 billion, or even 10 billion years ago. The farthest galaxies we can see emitted their light 13.8 billion years ago, but due to the universe's expansion, these galaxies are now about 46 billion light-years away. Even though we've peered deep into space, there's no evidence of a boundary. On the largest scales, the universe appears uniform, with no regions hotter or colder, or more crowded with galaxies than others. This uniformity suggests the universe is even larger than we can observe. While our technology has its limits, our imagination doesn't. It's natural to wonder what lies beyond the observable universe, even if such speculation doesn't give us clear answers. Just like a person sailing the ocean without encountering an edge because Earth is round, the universe might be similarly curved, finite, but without a boundary. Cosmologists test this idea by understanding geometry. On a flat surface, parallel lines stay parallel forever, while on a sphere, they eventually meet. Edwin Hubble tried to use this logic in the 1930s by counting galaxies to determine the universe's shape. Today, astronomers use tools like the Wilkinson microwave anisotropy probe to measure the universe's mass and energy, helping us understand whether the universe is flat, positively curved, or negatively curved. Scientists also examine the cosmic microwave background, the afterglow of the Big Bang, for signs of curvature. If space is curved, it would help us understand whether the universe is finite but without edges. The instruments scientists use, though powerful, have limits, making it challenging to determine the universe's true shape. So far, our observations suggest the universe appears flat, but this could simply be because we're not able to see its full shape. The flatness we observe sets a minimum size for the universe beyond what we can see, at least 37 trillion light-years in diameter. This is thousands of times larger than the observable universe, and that's just the smallest possible size. The universe could be much larger or even infinite. The idea of an infinite universe is hard to grasp, but as we continue to explore and learn, we may get closer to answering whether the universe truly has no limits. In 1980, Benoit Mandelbrot was one of the first to use computer graphics to visualize concepts that couldn't easily be drawn by hand. He introduced a new type of geometry, which he called fractal, from the Latin word for broken or shattered. Fractals are structures that look similar no matter how much you zoom in or out, always revealing more detail without ever becoming simpler. This creates endless complexity. Mandelbrot used computers to create the now famous Mandelbrot set, demonstrating the idea of fractals. He also noticed that similar patterns are found in nature, like in fern leaves, Romanesco broccoli, and even in the clustering of galaxies. He wondered if the entire universe could be a fractal. While the universe appears mostly uniform at the largest scales we can observe, the idea of fractal-like patterns beyond our observational limits remains intriguing. As we explore the cosmos, we encounter infinity at every turn. The universe is expanding, with galaxies moving away from each other, much like a loaf of bread rising in the oven. If the universe started from an infinite point, then our observable universe was just a small part of that infinite expanse. Over time, although the observable universe grows, it's really just a measure of how far light has traveled. This leads to the idea that while the physical universe is getting less dense as it expands, the observable universe is only a fraction of the whole. Galaxies beyond our local group are moving away at an average rate of 70 km//mpk. Looking into the future, if no new forces interfere, the universe will continue expanding. Galaxies will drift farther apart, stars will move away from each other, and eventually, the universe will enter a state called the heat death. This isn't a single event, but rather a gradual fading into cold darkness. The observable universe will keep expanding, and while it may become infinitely large, we'll only ever be able to explore a finite part of it due to the limits imposed by the speed of light and the expansion of space itself. Looking back in time, we see the universe contracting, becoming smaller, denser, and hotter. Eventually, it shrinks to a point where our understanding of physics breaks down. We know that beyond a certain point smaller than a Planck length, our physical models no longer work. The universe may have started expanding from an infinitely small, dense, and hot point, but we have no way to understand what that might have looked like. Cosmologists like Alan Guth and Andre Linde have suggested that what we observe might just be a small inflating region within an infinitely large universe. This idea, known as eternal inflation, suggests that our universe is one of countless bubble universes that form in an endless cosmic expanse. Each of these bubbles might operate under different physical laws, potentially leading to a multiverse, a collection of infinite universes. In this multiverse, each universe could have different physical constants, like gravity or particle mass, creating limitless possibilities. Our Big Bang might just be a small event in an infinite cosmic history, and the heat death of our universe might just be a detail within a much larger framework. Roger Penrose's idea of conformal cyclic cosmology suggests that when our universe becomes infinitely large and enters its heat death, it might actually mark the beginning of a new universe. In this view, the cycles of the universe repeat in a continuous loop, where the end of one universe gives rise to another. Beyond infinity lies the concept of endless possibilities. Whether through fractals, a multiverse, or an ever-repeating cosmic cycle, the universe challenges our understanding of space, time, and existence itself. According to various theories, our universe might be just one bubble in a vast cosmic sea where countless other universes exist, each with its own unique physical laws. British physicist Brian Cox has discussed how the concept of multiple universes fits within the framework of eternal inflation, a theory that builds on the Big Bang. In this theory, the universe we observe is just one of many bubbles in a frothy sea of space-time. These bubble universes are continuously being formed. The process starts when a region of space stops its rapid inflation. However, not all parts of space-time cease inflating at the same time. While one part of space cools down and forms a universe like ours, other regions continue expanding, leading to the constant creation of new bubble universes. Each of these universes might have its own set of physical laws, potentially very different from what we experience in our universe. To better understand the multiverse, imagine an immense library filled with an infinite number of books. Each book represents a different universe. In this infinite library, every possible combination of physical laws and outcomes exists somewhere. In one book, gravity could be slightly weaker, leading to taller creatures and grander buildings. In another, the speed of light could be slower, profoundly changing how energy moves in that universe. The differences between these universes go beyond just physical laws. Entirely different courses of history and evolution could unfold. For example, imagine a universe where the dinosaurs never went extinct, evolving into intelligent beings. Or consider a universe where matter is composed of entirely different elements, leading to stars and planets formed from dark matter instead of the substances we know. Each bubble universe might represent a different story in this cosmic library, and the possibilities are truly limitless. The multiverse theory challenges us to think beyond our own universe, exploring the idea that there are infinite variations of reality, each with its own unique laws, histories, and possibilities. Is there any evidence that our universe is part of a multiverse? Could we be one bubble in a cosmic sea of universes? In the book Endless Universe, Beyond the Big Bang, authors Paul Steinhardt and Neil Turok propose a radical idea. They suggest that the universe didn't start with a single Big Bang, but instead goes through endless cycles of cosmic events. This theory includes the possibility that our universe has collided with other bubble universes in the multiverse. In 2015, researcher Ranga Ramchari found unusual signals while studying the cosmic microwave background, which is the oldest detectable light in the universe. He proposed that these signals might indicate a collision between our universe and another. Although it's unclear whether this interaction was minor or significant, Cherry's work adds weight to the idea that our universe might be just one in a vast multiverse. The CMB is often called the afterglow of the Big Bang. It's like a snapshot of the universe's infancy, offering a glimpse of how the universe has expanded and evolved. When astronomers study the CMB, they see not only a uniform glow, but also a complex pattern of light and dark patches. These patches show tiny temperature differences that helped shape the large-scale structure of the universe. One mysterious feature in the CMB is known as the cold spot, an area of unusually low temperatures. One theory about this cold spot is that it might be a cosmic bruise, evidence that our universe came into contact with another universe. This idea suggests that such collisions between universes could leave detectable marks, offering potential evidence of a multiverse. In 2007, theoretical physicist Laura Massini-Houghton proposed a hypothesis about the cold spot. She suggested that it could be the result of our universe interacting with another universe. According to her theory, if multiple universes exist, they might occasionally collide, leaving behind detectable bruises in the form of anomalies like the cold spot. The gravitational pull from a nearby universe might have slowed down the expansion of our universe in that specific region, causing the cooler temperatures we see today. This idea aligns with Ranga Ramchari's 2015 findings, which also suggested that features in the CMB might be signs of a past collision with another universe. Both Massini-Houghton and Cherry believe that these interactions between universes could cause fluctuations in cosmic inflation, leaving scars or dents in the fabric of our universe. These hypotheses raise important questions about the history of our universe. One of the key ideas of inflation theory is that everything in the universe should be evenly distributed. However, the cold spot and other anomalies challenge this assumption, suggesting a more complex history where our universe may have interacted with others. Imagine the universe not just as a collection of stars, planets, and space, but as something alive. This idea, that the universe could be seen as a living entity, has intrigued people for centuries. It suggests that the universe is not just a machine made of lifeless parts, but more like a giant organism, with everything connected and working together. When we think of life, we often think of things like plants, animals, and humans. But what if life could be something bigger, something that includes the whole universe? The idea of the universe as a living entity invites us to picture every part of the cosmos, every star, planet, and galaxy as part of a greater system that grows, changes, and evolves over time. In a living organism, all parts work together to keep it alive and functioning. Your body, for example, is made up of different systems like your heart, lungs, and brain, each playing its role. Even though these parts are different, they all work together to help you survive. The universe, in this view, could be seen in the same way. Each star, planet, and galaxy might be like a part of a larger system, playing its role in the balance of the cosmos. This doesn't mean that the universe is alive in the same way that a human or an animal is. It doesn't have a brain or thoughts. But the idea suggests that the universe behaves in ways that are similar to living things. It constantly changes, adapts, and evolves. Just like cells in a body, galaxies and stars could be seen as parts of a much larger organism that is always in motion. One reason people see the universe as alive is because of the energy that flows through it. The universe is not a still, quiet place. It's full of movement and change. Stars are born, live for billions of years, and then end in dramatic explosions. Planets form and orbit stars, while galaxies spin and sometimes even collide. This constant movement and energy make the universe seem alive, as it's always in a state of change. In this way, the universe is not just empty space, it's full of activity and energy, always growing and evolving like a living organism. Just as living things grow and change over time, so does the universe. The universe began billions of years ago with the Big Bang, which started the expansion of everything we see today. Since then, the universe has been growing, with galaxies moving farther apart as space itself stretches. This expansion is still happening, and scientists believe the universe will continue to evolve for billions of years. In a way, the universe is always being born, growing, and changing. Stars and planets are created, and over time, new ones replace the old. This cycle of birth and death is similar to what we see in living organisms. In this sense, the universe is not a still thing, it's alive with change and growth. One important idea behind seeing the universe as a living entity is that everything is connected. Just like the parts of your body work together, all the parts of the universe may be connected in ways we don't fully understand yet. This idea is supported by modern science, especially in quantum physics. We know that particles can be connected or entangled even when they are far apart. This suggests that the universe might be more interconnected than we realize. If we think of the universe as a living entity, it encourages us to see ourselves as part of something much bigger. We are not separate from the cosmos. Instead, we are deeply connected to it, just as cells are connected to the body they belong to. This view can give us a sense of belonging, reminding us that we are a small but important part of a vast living system. In this view of the universe, the Earth is not just a planet floating in space, it's part of a larger living system, with life playing a central role. The idea of Gaia from ancient mythology suggests that Earth behaves like a living organism. All the different ecosystems on Earth, like forests, oceans, and the atmosphere, work together to support life. This idea can be expanded to the whole universe, with Earth playing its role in the grand system of the cosmos. From this perspective, life on Earth is not separate from the rest of the universe. Instead, it is part of the natural order of the cosmos. The Earth, with all its life, is like a cell in the larger body of the universe, playing its role in the ongoing cycle of creation and change. While the universe doesn't have a heartbeat or a mind, it acts in ways that remind us of living things. It is always in motion, growing, changing, and interacting. From the smallest particles to the largest galaxies, everything in the universe is part of a complex, connected system. This idea helps us see the universe as more than just a collection of distant stars and planets. It is an active, living system, with each part contributing to the whole. The concept of the universe as a living entity invites us to think about our place in the cosmos in a new way. It encourages us to see the bigger picture, realizing that we are part of something much larger and more connected than we often realize. Just like the cells in our bodies work together to keep us alive, we too are part of the universe's grand system of life and energy. One of the reasons people imagine the universe as a living entity is the patterns we see across different scales. For example, when we look at images of galaxies spinning in space, they sometimes reflect the patterns we see in natural systems on Earth, like the spirals of seashells or the way plants grow. These patterns suggest that the same forces shaping life on Earth might also be at work throughout the universe. At the smallest scale, cells in our body, especially nerve cells or neurons, look similar to the vast webs of galaxies that make up the universe. It's as if the universe itself has a structure, almost like a cosmic brain, where galaxies act like neurons in a much larger system. These patterns at different levels, from microscopic to cosmic, add to the idea that the universe might act like a living organism, growing and expanding according to natural laws. In living organisms, energy constantly flows to keep everything working smoothly. The same is true for the universe. Stars produce energy through nuclear fusion, which releases light and heat. This energy travels across space, affecting everything it touches. Planets like Earth absorb this energy and use it to support life. But the flow of energy doesn't stop there. When stars die, they release their materials back into the universe, which then become the building blocks for new stars, planets, and even life. This cycle of creation, death, and rebirth is much like the way energy flows through living systems. In this sense, the universe is not still, it is always moving, with energy constantly flowing and changing. Just as living things rely on energy to grow and survive, the universe depends on the flow of energy to keep evolving. Stars, planets, and galaxies all take part in this cosmic process, exchanging energy and helping to shape the structure of the universe. Another reason to think of the universe as a living entity is its ability to maintain balance. Just as the human body stays balanced through systems like the immune and nervous systems, the universe also seems to have mechanisms that keep it stable. For example, the laws of physics, such as gravity, work across the universe to maintain order. Gravity pulls objects together, helping stars form and planets stay in orbit. Even though the universe is expanding, gravity ensures that galaxies don't drift too far apart. In this way, gravity acts as a force that holds everything together, just like how living organisms have systems that keep them balanced. Additionally, the cosmic background radiation left over from the Big Bang is spread almost evenly across the universe. This radiation acts like a kind of cosmic temperature, helping to create the conditions needed for stars and galaxies to form. This balance between energy, matter, and physical laws keeps the universe working smoothly, much like the systems that keep living beings healthy and functioning. Some people believe that if the universe is alive, it might also have a form of awareness. In the same way that our brains are made up of billions of cells that work together to create consciousness, could the universe, made up of countless stars and galaxies, also have some kind of awareness? This idea doesn't mean the universe has thoughts or feelings like a person, but it suggests that consciousness might be spread throughout the universe in ways we don't yet understand. Some scientists and philosophers suggest that just as living organisms can sense and respond to their environment, the universe might also have a way of reacting to changes and keeping itself in balance. This raises the idea that consciousness is not something that only happens in the brain, but could be a fundamental part of the universe itself. If we accept the idea that the universe is a living entity, it raises interesting questions about the role of humanity. Are we just small, insignificant beings in a vast universe, or do we play a part in its larger system? In the same way that individual cells in your body each have a role to play, humans might also have a role in the bigger system of the universe. Our ability to think, learn, and explore may help the universe grow and evolve. By understanding the universe and our place in it, we become part of this larger system, helping it develop. This perspective can also encourage a greater sense of responsibility. Just as we take care of our bodies to stay healthy, we might also need to take care of the Earth and the universe around us. Less than 100 years ago, our understanding of the universe grew in ways we never expected. This happened when astronomer Edwin Hubble discovered that the Milky Way was not the only galaxy. He showed that our galaxy, which has about 200 billion stars, is just one of many in a universe filled with countless galaxies. This discovery revealed the true size and vastness of the universe. Over the past century, we have made incredible progress in learning about space. Cosmology, the study of the universe, has become a strong field of science. Scientists have achieved amazing things, like figuring out what distant stars are made of and how galaxies move. They've also learned how stars and planets are born and how they die, and they've gained insights into the structure of space and time. Thanks to these discoveries, we now see the universe in a way our ancestors never could. The universe is a place of great forces, energy, order, and chaos. But perhaps most astonishingly, parts of this universe have become aware of themselves. We live in a universe our ancestors couldn't have imagined, and it is now clear that understanding it requires new ways of thinking, leaving behind old ideas. Our journey starts by noting that the way we talk about nature often reflects a big metaphor that shapes how we think about the universe. Throughout history, Western science has been shaped by central ideas. At one point, people saw the universe as a great mind. Later, it was thought of as a great machine. This machine metaphor has been so tightly connected with science that many people believe the two are the same. But that's not the case, and today, this view no longer helps us understand the universe as it once did. There are signs that our thinking is changing, moving towards seeing the universe more like a living organism, something that grows, evolves, and renews itself. This new way of thinking could help us better understand the universe and give us a deeper sense of our place in it. Interestingly, many people throughout history have compared the universe to an organism, both in Western traditions and other cultures. We'll explore this idea more later. However, it's important to note that we're not saying the universe is an organism. The universe is simply what it is. Whether it is more like an organism or a machine is something people will feel differently about. How we see the universe may say more about us and our place in history than about the universe itself. Still, it's clear that our understanding of the universe is improving. As we learn more, it seems we can understand the universe better by thinking of it as something alive, rather than as a machine. To explore this further, we need to look at the historical influences that shaped Western science and how they still affect our thinking today. The story we'll discuss is a brief summary, but it helps us see the difference between earlier views and the idea of the universe as something that grows and evolves. The idea that the universe is like a great mind comes from early Greek philosophers around the 4th century BCE. Many cultures saw the world as alive and full of spirit. Greek thinkers were influenced by older religious ideas, which believed that everything in nature had a soul or spirit. One of the most important Greek thinkers, Plato, created a worldview called idealism. He believed that the physical world we see is just a reflection of a higher mental reality. In this view, everything in nature had purpose and acted with intention. Later, early Christian scholars, inspired by Greek philosophy, especially Plato's ideas, believed that the universe had a higher, perfect world beyond this one. This thinking supported the Christian belief in heaven. The universe's creative force, in their view, came from outside this world, is God. During the Middle Ages, Christian teachings explained everything about life, death, and the meaning of existence. Challenging the Church's authority was dangerous and could lead to exile or worse. The focus on the afterlife made people think the world they lived in was flawed and separate from God. In the 17th century, the philosopher René Descartes had a major impact on the development of science. He introduced the idea that mind and matter are separate, creating a boundary between religion and the new scientific thinking. This allowed scientists to explore the physical world more freely while leaving the mind and spirit to religion. As scientists made new discoveries, some of these ideas began to challenge religious teachings. However, many early scientists were still deeply religious. For instance, Isaac Newton, who helped develop the idea of the universe as a machine, believed that God had set the universe in motion, but then stepped back to let it run on its own. Over time, though, the success of the machine model led many scientists and philosophers to think that reality was made entirely of matter and the need for supernatural explanations faded. Soon, everything, including the mind, was seen as a result of physical processes. The machine metaphor became the dominant way of understanding the world, with little room for consciousness or meaning beyond biology. By the mid-19th century, Charles Darwin's ideas changed how people thought about life. Darwin and others showed that all life came from a common ancestor and had evolved over time. This new way of thinking challenged the traditional creation story. From this view, humans were seen as just another type of animal, not special in any divine way. Evolution was understood as the passing of genetic material from one generation to the next. Life seemed to follow physical laws, fitting well with the machine model of the universe. Animals, plants, and even humans were viewed as machines. Eventually, the universe itself was thought of as a machine, operating under unchanging natural laws without any purpose. Although humans seemed less important in the grand scheme of things, the machine view helped explain huge advances in medicine, anatomy, cosmology, and technology. It also gave stability to the worldview of modern, non-religious societies. The shift in how we see the universe is sometimes called the Copernican revolution. When people learned that Earth wasn't the center of the universe, it challenged both religious beliefs and the idea that human life held special importance in the cosmos. This shift pushed scientists and philosophers to promise never to assume that humans had a central or special place in the universe again. Instead, people began to find comfort in science, which gave them the ability to control nature and improve the world to meet their needs. This view was supported by the English philosopher Francis Bacon, who famously said, "Knowledge is power." Many modern thinkers believe that seeing the universe as a machine has shaped how we view the world today. While science freed people from religious control, it also made humans feel less central to the universe. As science advanced, the human mind, its goals, and its values seemed to become less important in the bigger picture. Some scholars argue that this way of thinking, without meaning or purpose, has led to feelings of separation from nature, other people, and the universe. But is seeing the universe as a machine the best way to understand reality? Is it the only way to explain the discoveries we've made? Over the past century, the machine view has been challenged by new ideas. These new ideas suggest that the universe might be better understood as something alive, like a living organism. We often think of the universe as a vast space filled with stars, planets, and galaxies. But what if the universe is more than that? Some believe that the universe might have its own kind of awareness or consciousness, and this idea has fascinated people for many years. The idea of a conscious universe isn't new. Philosophers and scientists from different times and places have asked if the universe itself could be alive in some way. Could it think or feel, even if it's on a level we don't yet fully understand? In our daily lives, we experience consciousness as something that belongs to living things. We are aware of our surroundings, we think, and we feel. But some theories suggest that consciousness might not be limited to living beings like humans and animals. These ideas propose that consciousness could be spread throughout the universe, in every star, planet, and even the space between them. This idea connects us to something much bigger. If the universe is conscious, then maybe we are all part of that consciousness. It could mean that our minds are not separate from the universe, but deeply connected to it. This changes how we think about our place in the universe. For many years, scientists have explored the universe to find answers to big questions. They study stars, galaxies, and the forces that hold everything together. But recently, some scientists and philosophers have started asking different kinds of questions. Instead of only asking how the universe works, they are asking if the universe could have a mind of its own. One of the most interesting parts of this idea is that it changes how we see ourselves. If the universe is conscious, then we are not small and insignificant. Instead, we become a part of something far bigger. Our thoughts and feelings could be part of the thoughts and feelings of the universe itself. Of course, this is just a theory. There's no solid proof that the universe is conscious, and many scientists are still trying to understand what consciousness even is. But that doesn't mean we can't think about it. Just like people long ago looked up at the stars and wondered what they were, we can look at the universe and wonder about its consciousness. There are many theories about how the universe might be conscious. Some suggest that the universe is like a living organism, with galaxies, stars, and planets working together in some way, just as our bodies are made up of tiny cells. Others believe that consciousness is something that flows through the universe, connecting everything. One theory that has gained attention is called panpsychism. This theory suggests that consciousness isn't just limited to living things like humans or animals. Instead, consciousness might exist in everything, even in the smallest parts of the universe, like atoms and particles. If this is true, then consciousness is everywhere and in everything. When we look at the stars at night, it's easy to feel small and disconnected. But if the universe is conscious, we might actually be deeply connected to it. Just like every part of our body is connected, every part of the universe could be linked through consciousness. This gives us a new way to think about the world and our place in it. Some thinkers even suggest that consciousness might be what creates the universe. They argue that without consciousness, there would be no one to experience the universe, and so the universe might not exist in the way we understand it. In this view, consciousness and the universe are deeply connected, and one cannot exist without the other. The idea of a conscious universe also makes us rethink time. We often think of time as something that moves in one direction, past, present, and future. But if the universe is conscious, maybe time isn't as simple as we think. Some theories suggest that consciousness might exist outside of time in a way that's hard for us to imagine. This could mean the universe doesn't experience time like we do, and that consciousness could be timeless. This brings up an important question. If the universe is conscious, what does that mean for us? Are we just small parts of a larger consciousness, or do we play a bigger role? Could our thoughts and actions affect the universe, just as the universe affects us? Some believe that if the universe is conscious, then everything we do and think could have an impact, even in ways we don't fully understand. This might mean our individual consciousness is part of a much larger network, stretching across the entire universe. As we explore this idea, it's important to remember that we don't have all the answers. The conscious universe theory is still just a theory, and we may never know for sure if the universe is truly aware of itself. But thinking about it can help us feel more connected to the world and bring a sense of wonder about the universe we live in. The idea of a conscious universe also connects to spirituality for many people. Different cultures have long believed that the universe, or the earth, is alive in some way, and that everything is connected through a shared energy or spirit. In these traditions, the idea of a conscious universe isn't new, it's something that's been believed for thousands of years. As we finish this introduction to this fascinating idea, let's take a moment to reflect on the possibility that we are not alone in our consciousness. The universe, vast and mysterious, might be more alive than we ever imagined. Thinking about this can bring a sense of peace and connection as we consider that we may be part of something much bigger than ourselves. Pandora's cluster is a group of stars and galaxies that formed from at least 4 different galaxy clusters after a huge collision in the distant past. In images of this cluster, red areas show X-rays, and the blue areas show where most of the mass is located. Interestingly, the blue mass is where there's no visible light. This is what we call dark matter. In fact, about 75% of the mass in Pandora's cluster is dark matter. Scientists believe dark matter makes up about 27% of the total mass in the universe, while most of the rest is something called dark energy. The strange part is that nobody really knows what dark matter or dark energy is. So, about 95% of the universe remains a mystery, even though we've been studying it for a long time. There are big unknowns at both the smallest and largest scales in the universe. It would be amazing if all these mysteries were connected by one simple idea, but we haven't found that idea yet. It's almost like the universe is playing tricks on us. One idea that tries to explain some of these mysteries is panpsychism, which suggests that consciousness might be a part of everything in the universe. The basic idea behind panpsychism is simple, but also controversial. Everything is conscious, from galaxy clusters to tiny particles. Even someone in a coma. It's complicated, but the cells in their body and the molecules within those cells may have some form of consciousness. What makes panpsychism interesting is how it explains certain mysteries. Maybe dark matter and dark energy don't really exist, and we just think they do because stars and galaxies choose to act a certain way. We can sense many things like sights, sounds, and smells. Of course, small particles don't sense things like we do, but they do have properties like electric charge that interact with their surroundings. Electrons are drawn to positively charged particles and pushed away by negative ones. You could think of this attraction and repulsion as a kind of awareness. Since this attraction changes depending on distance, it suggests that electrons have a point of view. You could say the same about almost anything that has properties and interacts with other things, even theoretical objects like magnetic monopoles or the strings in string theory. One reason panpsychism is so appealing is that it offers a way to explain some of the big mysteries of the universe. For example, we know that humans and animals are conscious, but we don't fully understand how consciousness comes to be. How do physical processes in our brain lead to awareness? Panpsychism provides an answer by suggesting that consciousness is present at a fundamental level, even in the smallest parts of the universe. In this view, consciousness doesn't just appear in complex beings like humans, it's always been there, even in the tiniest particles. This idea also challenges the traditional view that the universe is made up of 2 separate things, matter and the conscious mind. In the traditional view, these 2 things are very different, and it's hard to explain how they interact. But panpsychism suggests that matter and mind aren't separate, they're 2 sides of the same coin. Everything in the universe has both a physical and a mental side. Now, let's step back and think about the universe as a whole. The universe is vast, with billions of galaxies, each containing billions of stars and planets. It's hard to even imagine its scale. Panpsychism asks us to consider that the entire universe might be conscious in some way. Some people may find this idea strange, but others think it offers a new way to understand the universe. If everything in the universe has some form of consciousness, then the universe itself might be seen as a kind of giant mind, with different parts experiencing different things. This doesn't mean the universe has thoughts or feelings like we do, but it suggests the universe could have a deeper, more complex nature, one that includes consciousness at all levels, from the tiniest particles to the largest galaxies. Panpsychism can also help explain some of the biggest mysteries in modern science, like dark matter and dark energy. Scientists believe dark matter makes up about 27% of the universe, and dark energy makes up about 68%. Together, they account for 95% of the universe. But the strange thing is, we don't really know what dark matter or dark energy are. They don't interact with light or other things we can easily observe. Panpsychism offers a different way to think about these mysteries. What if dark matter and dark energy don't really exist as separate things, but are the result of conscious choices made by stars, galaxies, and particles? In this view, the universe might behave the way it does not because of mysterious forces, but because the parts of the universe are choosing to act in certain ways. Of course, this is just a theory, and it's not yet backed by scientific evidence, but it shows how panpsychism can offer new, creative ways of thinking about some of the biggest questions in science. One of the most interesting ideas in panpsychism is that consciousness plays a key role in the universe. In traditional science, consciousness is usually thought of as something that comes from complex brains like ours. But in panpsychism, consciousness is everywhere and is a fundamental part of reality. This raises some important questions. If consciousness is present throughout the universe, could it shape how the universe evolves? Could it influence how stars, galaxies, and planets form? Could consciousness play a role in the development of life? These are big questions, and we don't have the answers yet. But panpsychism invites us to think about the universe in a new way, one that doesn't separate mind from matter but sees them as connected. Of course, not everyone agrees with panpsychism. Some people think it's too far-fetched to believe that everything in the universe has consciousness. Critics argue that there's no solid evidence to support the idea, and it might just be wishful thinking. They believe that consciousness is something that only appears in complex beings, like humans, and doesn't exist in simple particles or objects. Others argue that even if panpsychism is true, it doesn't explain how consciousness works. Just saying that everything has consciousness doesn't tell us how consciousness arises or what it means to be conscious. These criticisms are important, but they don't take away from the fact that panpsychism offers a new and exciting way of thinking about the universe. It challenges us to rethink some of our most basic ideas and opens the door to new possibilities. When we think about evolution, we usually picture physical changes in living things over time, such as animals adapting to their environments, plants evolving to survive in different climates, and humans developing tools to thrive. But what if consciousness itself is part of this evolutionary process? Could consciousness be not just something that comes from evolution, but also a driving force that helps shape the future of life and the universe? Consciousness, at its simplest, is the awareness that living beings have of themselves and their surroundings. For humans, it means thinking, feeling, and making decisions. But even simpler life forms like animals and plants show signs of awareness in the way they sense and respond to their environment. Over time, life has developed more complex forms of consciousness, starting with the basic awareness of simple organisms, leading to the self-awareness and intelligence we see in humans today. Traditionally, we think of evolution as life adapting to survive better in its environment. Consciousness, in this sense, might have evolved as a tool for survival. For example, animals that are more aware of their surroundings are more likely to avoid danger, find food, and reproduce. But consciousness doesn't just help life survive. It also allows living beings to make choices and shape their own future. For humans, consciousness has played a huge role in our evolutionary journey. Unlike other animals, humans have developed self-awareness, the ability to think about ourselves, our actions, and our future. This has allowed us to change how we interact with the world in ways no other species can. Humans have used consciousness to invent tools, build complex societies, and shape our environment. Our ability to think ahead and plan for the future has led to advancements in technology, science, and culture. Consciousness has driven us to ask big questions about the universe, come up with new ideas, and improve how we understand the world around us. In this way, consciousness has become one of the most powerful forces in human evolution, helping us not only adapt to our surroundings but also change them. As consciousness keeps evolving, it has the potential to take life beyond just survival. In the past, evolution was driven by the need to survive and reproduce, but now, consciousness has opened up new possibilities. Instead of just adapting to survive, humans can now shape the world in more intentional ways. We can make choices that go beyond basic needs, like protecting the environment, exploring space, and using technology to improve the quality of life. This ability to think beyond survival suggests that consciousness could guide the next stages of evolution. Instead of being shaped only by natural selection, life could evolve through the conscious choices of intelligent beings. As humans continue to develop technology and learn more about the universe, consciousness might play an even bigger role in shaping the future of life. One of the most exciting ways consciousness might evolve is through technology. In the last century, humans have created technologies that have dramatically changed how we live. From computers to artificial intelligence, technology is becoming more and more a part of human life, and it is shaping the future of our species. In the future, technology could help us expand our consciousness in ways we can't even imagine. Some scientists believe that as technology advances, we may one day be able to enhance human consciousness with things like brain-computer interfaces or other tools that allow us to access more information, think more clearly, or even communicate in new ways. This could be the next step in human evolution, where consciousness isn't limited to the brain's natural abilities, but is expanded through technology. In this way, consciousness could evolve alongside technology, helping us explore new possibilities and push the limits of what it means to be aware. But the evolution of consciousness may not stop with humans. As we explore the universe, it's possible that we will find other forms of life that have their own types of consciousness. These life forms might have evolved in ways that are very different from us, with levels of awareness we can't even imagine. This raises the idea that consciousness might play a role in the evolution of the universe itself. Just as life has evolved on Earth, the universe as a whole may be evolving, with consciousness playing a central role. As more intelligent life forms develop, they might help guide the future of the universe, shaping it in ways we can't yet predict. Some scientists and thinkers have even suggested that the universe could be moving toward a state of greater consciousness, where intelligent life plays a key role in shaping the future of the cosmos. The connection between quantum physics and consciousness is a fascinating topic. At the same time, the idea of the universe working like a large neural network has gained attention. Neural networks are systems of connections similar to those in our brain, where information flows and changes over time. In this view, the universe could be thought of as a massive network, where everything is connected and consciousness plays a role in this connection. One of the most interesting ideas in quantum physics is the role of the observer. In many quantum experiments, particles don't seem to settle into a specific state until they are observed. Before that, a particle exists in a state of superposition, meaning it can be in many states at once. But as soon as it's observed, the particle seems to take on one definite state. This has led some scientists and philosophers to suggest that the act of observation might play a key role in shaping reality. If observing a particle changes its behavior, then maybe consciousness, which does the observing, is somehow linked to the way the universe works at a deep level. This idea raises questions about whether consciousness could be more than just a result of brain activity. The connection between quantum physics and consciousness is still debated, but some theories suggest that consciousness might come from quantum processes happening inside the brain. One idea is that the brain might work like a quantum computer, using the strange principles of quantum physics to process information. For example, quantum particles can exist in more than one state at the same time, and they can become entangled, allowing instant communication between distant particles. Some researchers believe these quantum effects might be happening in the brain, making complex thought and possibly consciousness itself possible. While this idea is still in its early stages, it raises an interesting question. Could consciousness be linked to quantum mechanics? If the brain works using quantum principles, it might explain why consciousness is so difficult to understand with traditional scientific methods. Quantum physics could offer new insights into how our minds work and how they connect to the universe. Another idea that links quantum physics and consciousness is viewing the universe as a neural network. A neural network is a system where individual units, called neurons, connect and interact with one another. In the brain, neurons send signals to each other, allowing us to think, feel, and process information. Some scientists believe the universe might work in a similar way. Just like the neurons in our brain, the basic particles of the universe could be connected in a vast network, always interacting and sharing information. In this view, the universe could be seen as a giant brain, where everything is tied together in a web of connections. This idea is supported by quantum physics, which shows that particles can be entangled across large distances. These particles stay connected no matter how far apart they are, suggesting that the universe might be more like a network than a collection of separate objects. If the universe is a massive neural network, then consciousness could be one of the key elements in this network. Just as neurons in the brain create our awareness and thoughts, the particles of the universe might work together to create a form of universal consciousness. This would mean that consciousness isn't just something that happens inside our brains, but rather something woven into the fabric of the universe. If quantum physics and consciousness are connected, it could change how we think about both the mind and the universe. One of the biggest mysteries in science is the hard problem of consciousness and the question of how physical processes in the brain lead to the experience of being aware. Quantum physics might offer a new way to approach this problem by suggesting that consciousness is not just the result of the brain's activity, but is also something more basic to the universe itself. This brings up many questions. For example, if consciousness is tied to quantum processes, does that mean all particles in the universe have some form of awareness? Could consciousness be spread across everything, from the smallest particles to the largest galaxies? Scientists and philosophers are still exploring these questions, and we are just starting to understand what they might mean. While the idea of linking quantum physics and consciousness is gaining attention, many scientists are cautious. Critics argue that just because quantum physics is strange and hard to understand, that doesn't mean it has anything to do with consciousness. They point out that there is no clear evidence that the brain works like a quantum computer or that consciousness comes from quantum processes. In fact, most neuroscientists believe consciousness can be explained by the activity of neurons in the brain without needing quantum mechanics. According to this view, consciousness comes from electrical and chemical signals in the brain, and while we don't fully understand it yet, there's no need for quantum explanations. Have you ever looked up at the stars and wondered how everything seems so perfect for life to exist? It's almost like the universe was created just for us. But is that really true? Could it be that the universe is fine-tuned for life? In this video, we'll explore what fine-tuning means, why it matters, and whether the universe was made for humans. First, let's talk about what fine-tuning means. When scientists say the universe is fine-tuned, they mean that the basic forces and conditions in the universe seem to be just right for life to exist. These include things like the strength of gravity, the charge of electrons, and the balance between matter and energy. If any of these were even a little bit different, life, at least as we know it, might not be possible. Think of it like building a house. You need the right materials and measurements for it to stand. If the walls are too weak or the roof is the wrong size, the house will collapse. In the same way, the universe has certain conditions that allow it to support life, and those conditions seem to be just right, as if someone planned it that way. One way to explain fine-tuning is with the story of Goldilocks and the Three Bears. In the story, Goldilocks tries different bowls of porridge, chairs, and beds until she finds ones that are just right. Similarly, the universe seems to have just the right conditions for life. For example, if gravity were a bit stronger, stars might burn out too quickly. If it were weaker, stars might never form. The balance of forces in the universe allows stars to shine, planets to form, and eventually life to exist. These conditions seem so precise that it makes you wonder, why is everything so perfectly balanced? Was the universe designed for life, or is it just a coincidence? Some people believe that fine-tuning is just a coincidence. They point to the anthropic principle, which says the universe has to be this way because if it weren't, we wouldn't be here to notice it. In other words, we exist in a universe that supports life because if it didn't, we wouldn't be alive to ask the question. While this idea seems logical, it doesn't really answer the bigger question, why is the universe like this in the first place? So, was the universe made for us? This is where things get interesting. Some people believe that the fine-tuning of the universe is evidence of a higher purpose, that the universe was created by a higher power or designed to support life. This idea is known as the design argument. According to this view, the universe isn't just a random accident, but something created with intention. Others think that while the universe seems fine-tuned, it could just be a natural outcome of the laws of physics. In this view, the universe didn't have to be made for us. Instead, life adapted to the universe's conditions. Just like plants and animals adapt to their environments, life on Earth may have adapted to the universe's conditions, not the other way around. Another idea that might explain fine-tuning is the multiverse theory. This theory suggests that our universe is just one of many. In some of these universes, the conditions might be too extreme for life to exist. In others, they might be similar to ours or completely different. If there are countless universes, it's possible that we just happen to live in one where the conditions are right for life. Think of it like a lottery. The odds of winning are very low, but if millions of people are playing, someone is bound to win. The multiverse theory suggests that we're living in the universe that won the lottery by having the right conditions for life. To understand the idea of fine-tuning better, let's look at how delicate the balance of the universe really is. The forces that govern our universe, like gravity, electromagnetism, and the strong nuclear force, all need to be within a very narrow range for the universe to exist as it does. Take gravity, for example. If gravity were even slightly stronger, stars would burn out much faster. This would leave less time for planets to form, and life, as we know it, wouldn't have had a chance to develop. If gravity was slightly weaker, stars and planets might not have formed at all, and there would be no life anywhere. The fact that gravity is just right is one of the key reasons we're able to exist. Another example is the balance between matter and antimatter. After the Big Bang, equal amounts of matter and antimatter were created. If this balance were perfect, they would have destroyed each other, leaving nothing behind. But there was just a little more matter than antimatter, allowing galaxies, stars, and planets to form. This small imbalance made it possible for everything we see around us to exist. Carbon is another critical element for the fine-tuning of the universe. All known life is based on carbon, and without it, life as we know it wouldn't be possible. The way carbon forms in stars is a perfect example of fine-tuning. Inside stars, lighter elements like hydrogen and helium fuse together to form heavier elements. But for carbon to form, very precise conditions are needed. If the forces inside stars were slightly different, there wouldn't be enough carbon, and without carbon, there would be no life. While it's easy to see the universe's fine-tuning as evidence that it was made for us, another way to think about it is that life adapted to the universe. Over billions of years, life on Earth evolved to fit the conditions of our planet and the universe. Just like animals adapt to their environments, life may have simply evolved to survive in the conditions of the universe. In this view, life wasn't designed to fit the universe. Instead, the universe's conditions allowed for life to evolve. Over time, life forms developed to match the environment they found themselves in. Life evolved to fit the universe, not the other way around. Another idea is that the fine-tuning of the universe could simply be the result of chance. Some scientists think that the universe's conditions were determined randomly when it began. In this case, we just happen to live in a universe where the conditions are right for life. If the universe had different conditions, life might not exist, or life might exist in a form we can't even imagine. This opens up the possibility of life forms that don't rely on the same forces or conditions that we do. One question that comes to mind is whether the universe is fine-tuned only for humans, or if other forms of life, very different from our own, could exist somewhere else. Life as we know it depends on water, carbon, and certain chemical reactions. But what if there are other kinds of life that don't need these things? For example, scientists have considered the possibility of silicon-based life, which could exist in conditions very different from Earth's. This raises the question, could the universe support life forms that are completely different from anything we've ever seen? If so, the fine-tuning of the universe might not be just for humans or Earth-based life, but for many kinds of life we haven't yet discovered. The idea of fine-tuning has sparked philosophical and spiritual discussions. Some see fine-tuning as proof of a higher purpose or design. They believe the universe was created intentionally with life in mind. This view suggests that there is a greater reason behind the existence of life, and the universe's conditions are part of a plan. Others take a more scientific approach. They argue that the universe's conditions happen to support life without any intentional design. This debate highlights one of the biggest questions we face, whether there's a reason behind the universe's fine-tuning or if it's just a random occurrence. No matter how you view fine-tuning, it makes us think deeply about our place in the universe. The precise conditions for life remind us how special and fragile life is. Whether the universe was made for us or we just evolved in it, the fine-tuning of the universe makes us curious about the nature of reality and our role in it. It encourages us to keep asking questions about the universe, exploring new ideas, and seeking a better understanding of the world around us. This curiosity is at the heart of science, philosophy, and spirituality. By exploring these big questions, we can gain a greater appreciation for the universe and our place in it. The question of the meaning of life is one that people have asked for thousands of years. From ancient philosophers to modern thinkers, we've all wondered at some point, why are we here? What's the purpose of it all? The search for meaning is something everyone experiences in their own way. While there may not be one single answer, asking the question is at the heart of philosophy and spirituality. In this video, we'll explore the idea of the meaning of life, how it's connected to consciousness, and why we all think about it. From the moment we become aware of ourselves, we start to wonder about life's purpose. For some, meaning comes from personal connections like family, friendships, and love. For others, it's found in achievements, helping others, or learning about the world. Some people find meaning through spirituality, believing that life is part of a greater plan or order. There's no single answer to the question of life's meaning. It's personal and can change depending on where we are in life and what we're going through. The search for meaning is a journey that evolves as we grow. Our awareness of ourselves and the world around us is at the core of our search for meaning. It's what allows us to reflect on our lives, ask big questions, and wonder why we are here. Without consciousness, we wouldn't be able to think about life's purpose at all. Consciousness lets us think beyond just our basic needs. While other animals are focused on survival, humans have the unique ability to ask why we exist. We can imagine different futures, create goals, and explore ideas that go beyond just living day to day. This ability to think deeply is why consciousness is closely tied to the search for meaning. Our awareness of life, time, and even death leads us to ask, what should we do with the time we have? Consciousness lets us reflect on the bigger picture of existence. Throughout history, different cultures and philosophies have offered various views on the meaning of life. For some, life's purpose is about finding happiness, joy, and peace in what we do. For others, it's about growth and learning, improving ourselves, and becoming better. Some spiritual traditions see life as a journey toward a higher understanding or connection with the universe. In Buddhism, for example, the meaning of life is tied to finding inner peace and understanding suffering. In Christianity, it's often seen as living in line with God's plan. Other philosophies, like existentialism, say that life doesn't come with a built-in meaning, and it's up to each person to create their own purpose. In this view, meaning isn't given to us. It's something we choose through our actions and decisions. One interesting idea is that consciousness itself might be the key to creating meaning in life. Because we are aware of ourselves and the world, we have the power to define what matters to us. Our thoughts, feelings, and experiences allow us to shape our own sense of purpose. Some people find meaning through relationships, where connection with others brings fulfillment. Others find it through work or creativity, feeling a sense of purpose when they contribute something to the world. Consciousness allows us to choose what's important to us, giving each person the freedom to create their own path in life. In this sense, the meaning of life isn't something that's given to us from the outside, it's something that comes from within. Our awareness of life's possibilities lets us decide what matters, whether that's love, knowledge, or something else unique to each person. While everyone's sense of meaning is different, there's also the question of whether there is a universal meaning to life. Is there a purpose that applies to everyone, or is it up to the individual? This question has been debated by philosophers, spiritual teachers, and thinkers for centuries. Some believe that there is a higher universal purpose behind life, one that connects all living beings and the universe. In this view, life is part of a greater whole, and each person plays a role in the big picture. For some, this idea brings comfort knowing their life has a purpose that fits into something larger. Some people believe that the meaning of life isn't the same for everyone. They think each person has to find their own meaning based on their own experiences, beliefs, and values. In this view, there is no single answer to the meaning of life. Instead, there are many different ways to find purpose. One reason the question of life's meaning is so powerful is because it touches on the mystery of existence. Why are we here? How did life begin? What happens when life ends? Consciousness allows us to ask these questions, but it doesn't always give us clear answers. For some, the mystery itself gives life meaning. Not having all the answers can make us feel a sense of wonder and curiosity about the universe. It pushes us to keep learning and seeking understanding. In this way, consciousness isn't just a tool for thinking about meaning, it's part of what makes life feel meaningful in the first place. A common way people find meaning is through their experiences. This can be as simple as spending time with loved ones, enjoying nature, or creating something new. The key to finding meaning through experiences is paying attention to the present moment and noticing the importance of the little things in life. For example, sharing a laugh with a friend, watching a sunset, or overcoming a personal challenge can give us a sense of fulfillment. These moments might seem small, but they can carry deep meaning because they remind us of the beauty and richness of life. Consciousness allows us to fully feel these moments, making them important parts of our life's journey. Sometimes, meaning comes from facing difficulties. Overcoming challenges, whether big or small, can give us a sense of purpose and growth. It helps us see how strong we are and can lead to a deeper appreciation of life. Another way people find meaning is through personal growth. Life is a journey where we are always learning, changing, and becoming more of who we are. Personal growth doesn't always mean achieving big goals. Sometimes it's about learning from mistakes, becoming kinder, or understanding ourselves better. When we grow as individuals, we often feel a stronger sense of purpose. Consciousness helps with this because it allows us to reflect on who we are, what we've been through, and where we want to go. By thinking about ourselves and our experiences, we can see how far we've come and set new goals for the future. Personal growth is about becoming the best version of ourselves, and this process can bring deep satisfaction and meaning. Whether it's learning a new skill, improving our relationships, or finding inner peace, personal growth adds layers of meaning to our lives. One of the most powerful ways to find meaning in life is through connection, our relationships with others, and the bonds we build. How consciousness lets us build strong connections with the people around us, whether they are family, friends, or even strangers. When we connect with others, it often gives us a sense of purpose. Helping someone, sharing our thoughts, or just being there with another person can make us feel like we belong and that our lives have meaning. These connections remind us that we're not alone in the universe. We are part of a network of relationships that bring joy, support, and understanding. Beyond relationships with people, some find a connection to the natural world. Being in nature, whether walking in the forest, swimming in the ocean, or watching animals, can remind us of the beauty and wonder of life. For many, spending time in nature brings peace and helps them feel connected to the larger world around them. Creativity is also a way that many people find meaning. Whether it's painting, writing, building, or playing music, creating something can bring fulfillment and purpose. Consciousness allows us to share our thoughts, ideas, and emotions in unique ways, and creating something helps us connect more deeply with ourselves and the world. But creativity isn't only about art. It can be found in everyday life, like solving problems, coming up with new ideas, or finding ways to help others. Consciousness lets us imagine new possibilities and make them real. In this way, creativity helps shape our world and brings meaning through the things we create, the ideas we explore, and the stories we tell. For some, creating something like a book, a song, or a piece of art feels like leaving a mark on the world. It becomes a way to contribute to life's ongoing story and leave something behind. One special thing about human consciousness is that we can think about the future. We're not just stuck in the present moment. We can imagine what's next, set goals, and work towards things we want to achieve. This ability to plan and dream gives us a sense of direction and purpose. Whether it's planning our next career move, dreaming about starting a family, or thinking of ways to make the world better, our consciousness helps us imagine what's possible and work toward it. Thinking about the future also shapes our sense of meaning because it gives us hope and purpose. Perhaps the most empowering part of the meaning of life is that we have the freedom to create our own meaning. Our consciousness gives us the ability to reflect on life and choose what matters to us. Whether it's through love, creativity, personal growth, or helping others, the meaning we find comes from our own choices and experiences. For centuries, people have viewed Earth as a planet full of life. However, the idea that the Earth itself might behave like a living organism is something that challenges our way of thinking. This concept is called the Gaia hypothesis, a theory that suggests Earth is not just a collection of plants, animals, oceans, and mountains, but that it functions as a single self-regulating system, almost like a living being. The Gaia hypothesis was proposed in the 1970s by British scientist James Lovelock. The theory is named after Gaia, the ancient Greek goddess of the earth. His idea was simple: that our planet Earth behaves like a living organism, working to maintain the right conditions for life. According to the Gaia hypothesis, all living and non-living parts of Earth work together to create a balanced, stable environment. This includes everything from plants and animals to the atmosphere, oceans, and even the rocks beneath our feet. The theory suggests that life on Earth doesn't just adapt to its environment, it actively helps shape and control it. In other words, life and the planet are interconnected in a way that keeps Earth habitable. The Gaia hypothesis suggests that Earth has self-regulating systems that work like the body's systems. Just as your body controls its temperature, heart rate, and breathing to keep you alive, the Earth controls things like temperature, ocean salinity, and oxygen levels to maintain life-friendly conditions. For example, let's think about oxygen. Plants and trees release oxygen into the air through photosynthesis, which animals and humans need to breathe. If oxygen levels become too low, it could threaten life on Earth. According to the Gaia hypothesis, Earth's systems, including plants, help regulate oxygen levels to keep them stable. Another example is the temperature of the Earth. Over millions of years, Earth's temperature has stayed within a range that allows life to survive, even though the sun has become hotter. This stability could be due to the Earth's ability to regulate its own temperature like a thermostat. The planet does this through natural processes, such as the absorption of carbon dioxide by plants and oceans, which help to cool the planet when necessary. These are just a few examples of how the Earth may regulate itself, working to keep conditions balanced for life. One of the key ideas in this hypothesis is that living things like plants, animals, and microorganisms, and non-living things like air, water, and soil all work together to create a healthy planet. Each part of the Earth plays a role in maintaining the environment, just like each part of your body helps keep you healthy. For instance, trees take in carbon dioxide from the air and release oxygen. This helps regulate the levels of gases in the atmosphere. Meanwhile, the oceans absorb large amounts of carbon dioxide, helping to reduce the amount in the atmosphere and control the planet's temperature. In this way, life on Earth isn't just a passive part of the environment. It plays an active role in shaping the planet, contributing to the processes that keep the environment stable and suitable for living things. In turn, the Earth's natural systems provide the conditions that allow life to thrive, creating a feedback loop where life and the planet support one another. The Gaia hypothesis suggests that Earth behaves like a living organism, but does that mean Earth is truly alive? According to Lovelock, the hypothesis doesn't claim that Earth is alive in the same way humans, animals, or plants are. Instead, it proposes that Earth functions like a living organism because it is able to maintain its own balance and keep conditions right for life. In this sense, Earth might not have consciousness or emotions, but it does have systems that respond to changes and help keep the planet stable. This hypothesis also reminds us of the delicate balance needed to keep Earth healthy. If Earth is like a living system, then human actions that damage the environment, such as pollution, deforestation, and the burning of fossil fuels, can throw that system out of balance. For example, by releasing too much carbon dioxide into the air, humans are contributing to global warming, which affects the Earth's ability to regulate its temperature. This could lead to changes that make the planet less stable and less hospitable to life. Understanding Earth as a living system can inspire a sense of responsibility. Just as we take care of our bodies by eating well and staying healthy, we need to take care of our planet to keep it functioning properly. This hypothesis helps us see that all life on Earth is connected, and what we do to one part of the planet can affect the whole system. The Gaia hypothesis also highlights the role of life in regulating the Earth's environment. In this view, life is not just a passenger on a lifeless planet. Rather, it plays an active role in shaping and maintaining the environment. For example, consider the role of phytoplankton in the oceans. Phytoplankton are tiny organisms that live near the surface of the ocean and produce oxygen through photosynthesis. They'd also help cool the Earth by releasing a chemical called dimethyl sulfide, which encourages cloud formation. These clouds reflect sunlight and help regulate the planet's temperature. In this way, tiny life forms in the ocean contribute to the global climate system. Similarly, forests play a huge role in regulating the Earth's climate. Trees take in carbon dioxide and release oxygen, helping to keep the atmosphere in balance. Forests also play a role in the water cycle by absorbing and releasing water, which helps regulate rainfall and maintain ecosystems. These examples show how life on Earth is not just adapting to the environment. It's actively shaping the planet to maintain conditions that support life. In this way, the Gaia hypothesis suggests that life and the environment are deeply interconnected and that both work together to create a stable, balanced system. Another important aspect of the Gaia hypothesis is the role of microorganisms in maintaining Earth's balance. Microorganisms are tiny living organisms, such as bacteria and fungi, that play a crucial role in many of the Earth's systems. For example, in the nitrogen cycle, certain bacteria in the soil help convert nitrogen from the air into forms that plants can use to grow. Without these microorganisms, plants would struggle to get the nutrients they need, which would disrupt ecosystems and food chains. These tiny organisms are an essential part of Earth's life support system, helping to maintain the balance of nutrients in the soil and atmosphere. Microorganisms also play a key role in breaking down organic matter and recycling nutrients. When plants and animals die, microorganisms break down their bodies, returning vital nutrients to the soil. This process helps sustain plant life and supports the entire food chain. In this way, microorganisms are like the Earth's recycling system, ensuring that nothing goes to waste and that life can continue to thrive. These examples show that even the smallest forms of life play an essential role in maintaining the balance of Earth's systems, further supporting the idea that the planet functions as a unified, living system. While the Gaia hypothesis has inspired a lot of people, it has also faced criticism from some scientists. Critics argue that the Earth doesn't intend to regulate itself, and that what we see as self-regulation is just a result of natural processes working by chance. They point out that life on Earth has survived through periods of extreme change, such as ice ages and mass extinctions, which suggests that the planet doesn't always maintain perfect balance. However, supporters of the Gaia hypothesis argue that the Earth's ability to recover from these extreme events actually supports the idea that it acts like a living system. Just as a living organism can survive injuries and heal over time, the Earth has shown resilience in the face of major disruptions. For example, after the extinction of the dinosaurs, life on Earth eventually bounced back and new species emerged, filling the gaps left behind. This shows that the planet has the ability to adapt and continue supporting life, even after dramatic changes. Supporters also point to modern environmental challenges as a reason to take the Gaia hypothesis seriously. As human activity causes changes in the environment such as climate change, deforestation, and pollution, Earth's natural systems are being pushed to their limits. If we understand Earth as a living system, we can see how important it is to protect the processes that keep the planet in balance. In this way, the Gaia hypothesis encourages a more holistic approach to environmental conservation, one that recognizes the deep connections between life and the environment. As we explore the mysteries of consciousness and the universe, one name of Erwin Schrödinger often comes up. Schrödinger was a physicist best known for his contributions to quantum mechanics, especially the famous thought experiment called Schrödinger's cat. But beyond his work in physics, Schrödinger had a deep interest in the nature of consciousness and how it might connect to the universe at large. In fact, Schrödinger developed a philosophical idea that is still discussed today, known as unified consciousness. This idea suggests that consciousness is not something that belongs to individual beings alone, like humans or animals. Instead, consciousness might be something that is shared by everything in the universe. Schrödinger's theory is an attempt to connect the strange behavior of particles in quantum mechanics with the mysteries of the mind and consciousness. Before knowing about Schrödinger's idea of unified consciousness, it's important to have a basic understanding of quantum mechanics. Quantum mechanics is the science that deals with the behavior of very small particles, such as electrons and photons, which make up the building blocks of everything in the universe. The strange thing about these particles is that they don't follow the same rules that larger objects do. For example, in the quantum world, a particle can exist in multiple places at the same time. This idea is called superposition. Particles can also be entangled, which means that if you affect one particle, it instantly affects another particle, even if they are far apart. This has led scientists to believe that, at a very small scale, everything in the universe is connected in ways that are difficult to fully explain with everyday logic. Schrödinger was one of the early pioneers of quantum mechanics, and he was deeply curious about what these strange behaviors might tell us about reality. But he was also interested in a different mystery, which was consciousness. Now, consciousness is something we experience every day. It's the feeling of being aware, of thinking, feeling, and sensing the world around us. But despite how common consciousness is, we still don't fully understand what it is or how it works. One of the biggest questions in science is how the brain, which is made up of physical cells, produces consciousness. How do chemical and electrical signals in our brains lead to the experience of being aware? This is often called the hard problem of consciousness, and it remains one of the biggest mysteries in both science and philosophy. Schrödinger believed that the answers to this question might lie in quantum mechanics. He had a deep interest in consciousness and its connection to the universe. Schrödinger proposed a theory that challenges the way we usually think about the mind. He believed that consciousness is unified, meaning that there is only one shared consciousness in the entire universe. This idea, known as unified consciousness, suggests that the division we feel between our individual minds and the rest of the world is not real. Instead, Schrödinger argued that the consciousness each of us experiences is just a part of a single greater consciousness that exists across all living beings and possibly beyond. Unified consciousness is a philosophical concept that Schrödinger developed based on his study of both quantum mechanics and ancient Eastern philosophies. The core idea is that the consciousness we experience is not separate or unique to each individual. Rather, it is shared, and all beings are part of one larger, unified mind. In our everyday experience, it seems like we each have our own separate thoughts, feelings, and awareness. But Schrödinger believed this was an illusion. He suggested that all individual consciousnesses are actually connected, like different branches of the same tree. While it feels like we are separate from one another, we are all drawing from the same source. In his view, what we see as our personal thoughts and experiences are just different parts of this one shared consciousness. This doesn't mean that we lose our sense of identity. Instead, it suggests that our awareness comes from a larger, universal mind that unites all living things. Schrödinger's idea of unified consciousness was simple but radical. He believed that consciousness is not something that belongs to individual beings alone, but rather, it is something that is shared by all living things. In Schrödinger's view, the consciousness we experience as individuals is just one small part of a much larger, unified field of consciousness that spans the entire universe. In other words, there is only one consciousness in the universe, and every living being is part of it. Schrödinger believed that the idea of separate, individual consciousnesses is an illusion. While it feels like we each have our own private minds, in reality, we are all connected by the same underlying consciousness. This idea of a shared consciousness ties into the principles of quantum mechanics. Schrödinger was especially influenced by the curiosity of entanglement, where two particles can be connected in such a way that changes in one particle instantly affect the other, no matter how far apart they are. Schrödinger saw this as evidence that the universe is deeply interconnected. Just as particles are linked through entanglement, Schrödinger believed that consciousness is also interconnected across the universe. Schrödinger's theory of unified consciousness is deeply connected to his work in quantum mechanics. Quantum mechanics, the branch of physics that studies the smallest particles of the universe, shows us that the world at its smallest levels behaves in strange and unexpected ways. Schrödinger believed that the weirdness of the quantum world could help explain the nature of consciousness. One of the most important ideas in quantum mechanics is entanglement. This is when two particles become connected in such a way that they can instantly affect each other, even when they are far apart. Schrödinger thought that this deep connection between particles might also apply to consciousness. Just as particles are linked together, Schrödinger believed that all consciousness could be connected, forming one unified whole. He also found the idea of the observer in quantum mechanics very important. In quantum experiments, particles don't seem to take on a definite state until they are observed. This suggests that the act of observing, an action that requires consciousness, can influence reality. Schrödinger believed that this connection between observation and reality hinted that consciousness might be more fundamental to the universe than we thought. Schrödinger's ideas weren't influenced only by science. He was also deeply inspired by Eastern philosophies, particularly those found in Hinduism and Buddhism. In these spiritual traditions, there is a belief that all living beings share a common consciousness, and the idea of a separate self is seen as an illusion. In Hinduism, the concept of Brahman refers to the ultimate reality that is present in everything. According to this view, the individual self or Atman is not separate from Brahman, but is a part of it. This idea strongly influenced Schrödinger's belief in a unified consciousness. Similarly, Buddhism teaches that everything in the universe is interconnected and nothing exists independently. Schrödinger saw parallels between these teachings and the discoveries of quantum mechanics. He believed that, just as quantum mechanics shows us that everything in the universe is connected at a deep level, these ancient philosophies reveal that our minds are connected in a similar way. If his idea of unified consciousness is correct, it means that our experience of being separate, individual minds is not the full story. In reality, we are all part of a much larger whole. Our thoughts, emotions, and awareness come from this shared consciousness, even though it feels like they belong only to us. Imagine a vast ocean. Each individual wave that rises on the surface of the ocean might seem separate from the others, but they are all made of the same water. In the same way, Schrödinger believed that each person's experience of consciousness is like a wave on the surface of a greater unified mind. This doesn't mean that our personal thoughts and feelings are unimportant. Rather, it suggests that we are connected to something much bigger than ourselves. Our minds are like small parts of a larger whole, and when we are conscious, we are experiencing just one aspect of this greater shared awareness. Another key idea in quantum mechanics that influenced Schrödinger's thinking is the role of the observer. In many experiments, particles don't seem to take on a definite state until they are observed. Before they are observed, they exist in a state of superposition where they can be in multiple states at once. It is only when an observation is made that the particle chooses one specific state. This idea, that reality might depend on whether or not it is being observed, has led some to suggest that consciousness plays a fundamental role in shaping the universe. Schrödinger believed that if consciousness plays a role in determining the state of particles, then consciousness might be much more important to the universe than we previously thought. This led him to propose that consciousness is not just a byproduct of the brain, but is a fundamental part of the universe itself. While Schrödinger's theory of unified consciousness is fascinating, it is also met with skepticism. Some scientists argue that there is no clear evidence to suggest that consciousness is shared across the universe. Many researchers believe that consciousness arises from the brain's complex activity and that it is a personal experience that cannot be spread across the universe. Others believe that even if quantum mechanics and consciousness are connected, it doesn't necessarily mean that all consciousness is one. They argue that while quantum mechanics might reveal a new way of thinking about reality, it doesn't automatically lead to the idea of a single unified consciousness.